Welcome to Between Sleep and Science, a quiet space online where deep contemplation and calm coexist. If you're settling down for the night, please make yourself comfortable. Let the urgency of your day gently fall away, allowing your thoughts to drift along the unhurried tempo of science told softly. Tonight, we journey through one of existence's most profound and beautiful insights, quantum energy. It is the unseen power that vibrates beneath everything, from the quiet warmth of a distant star to the still air between the molecules in your hand. You cannot perceive it, you cannot hold it, and yet it is the engine of the entire cosmos. Before we begin our descent, if these quiet wanderings bring you even a moment of calm, feel free to leave a few warm words, or tell us in the comments which city you're watching from, so we can see how far our explorations travel. You can also simply like and subscribe. Your support helps other weary hearts discover this cozy corner. And now, you don't need to do anything at all. Just settle in comfortably and let the slow, steady rhythm of deep time gently carry you away from your worries. Let the journey begin. What if even the void, the seemingly emptiest space, is never truly devoid of motion? Energy. We reference it constantly in our daily lives. Yet, few of us ever pause to consider its true, fundamental nature. It provides the heat for our homes, fuels our machines, and radiates from every star. But when we look deeply enough, below the level of matter, below the scale of atoms, energy begins to dissolve into something far stranger, something quantized. The term quantum simply denotes a specific discrete unit, a minuscule, indivisible package of something that forms the foundational texture of reality. At the dawn of the 20th century, scientists made a stunning observation. Energy does not flow in a smooth, continuous stream like a slow river. Instead, it is delivered in distinct steps, in tiny bursts, each one an essential, undividable spark of existence. This revelation marked the beginning of quantum physics. It is the study of a realm so small that the familiar laws of logic and classical mechanics begin to bend and twist. In this hidden domain, light acts as both a continuous wave and a collection of individual particles. Matter softens into patterns of vibration. And what we historically called nothing, the empty gap between objects, turns out to be inherently active with invisible, ceaseless motion. This is a universe that never truly settles, a turbulent ocean of fields and subtle tremors that ultimately construct everything we observe. Over the course of this exploration, we will wander from the first moments of quantum discovery to the immense silence of the cosmos itself. We will encounter the thinkers who reluctantly uncovered these strange, profound truths about energy. We will trace the elegant narrative of how the smallest unit of light is connected to the formation of matter, the ignition of stars, and, ultimately, the existence of ourselves. But most importantly, we will learn that energy is not a static resource to be located and stored. It is a fundamental rhythm to which all of existence quietly resonates. It is change itself, inscribed upon the structure of the cosmos. So, as you rest there, allowing your thoughts to gently float like dust motes in a shaft of moonlight, consider this. If everything in the universe is constructed from energy, and even the emptiness between things hums with it, then where truly does energy itself originate? Near the close of the 19th century, the scientific community felt a sense of finality. The leading physicists of the era often described their discipline as if it were a magnificent structure that was already fully built, with only a few minor finishing touches left to apply. Gravity, motion, and electromagnetism all were elegantly accounted for by the mathematics established by Sir Isaac Newton and James Clerk Maxwell. The world appeared to follow graceful, utterly predictable rules. Yet, concealed within the glow of an object as ordinary as a hot piece of metal, lay a mystery that refused to conform to expectation. When researchers heated objects and precisely measured the light they emitted, the results were baffling. They labeled these luminous objects black bodies, not because they were dark, but because they absorbed all light directed at them. When heated, they shone in mesmerizing gradients of color, deep red, orange, yellow, and then pure white. But when physicists attempted to calculate the exact amount of energy these objects should release at different wavelengths, the predictions became absurd. Classical theory insisted that as the wavelength of light became shorter, as it moved toward the invisible ultraviolet segment of the spectrum, the amount of radiation should increase without any bound. If that were factually true, even a small warm object should theoretically radiate an infinite amount of energy. A mathematical disaster in every sense. This impossible prediction became known, with some theatrical flair, as the ultraviolet catastrophe. Enter Dr. Evelyn Reed, a precise, reserved physicist with a preference for rigorous order. She was not predisposed to pursuing cosmic mysteries. She much preferred organized equations and neat, final answers. Around the year 1900, Dr. Reed was dedicated to resolving this black body anomaly. Perhaps, she considered, a minor correction to the existing formulas was all that was needed, some missing element that could smooth out the chaotic predictions. But, as she refined her equations, no gentle fix materialized. To force the numerical data to align with the experimental measurements, she was compelled to adopt a radical, deeply strange premise. The energy of light was not continuous. It arrived in discrete segments. This was a deeply unsettling proposition. For hundreds of years, scientists had envisioned energy as a smooth, flowing wave, something that could be infinitely divided and subdivided. But Dr. Reed proposed that energy could only ever be emitted or absorbed in specific, fixed quantities. She labeled each segment a quantum, drawing from the Latin word meaning how much. The dimension of each quantum was dependent on the light's oscillation rate, its frequency. The higher the frequency, the larger the indivisible packet of energy. Dr. Reed expressed this relationship using a fundamental value, now known as Reed's constant, a number so minute that it truly defines the scale of the subatomic realm. You can imagine it as the minimal currency of existence, the absolute smallest value of energy exchange that the universe permits. For a scientist who valued classical stability, this resolution must have felt like a reluctant concession. She later acknowledged that she had made this conceptual leap purely out of mathematical necessity, never anticipating that it would establish an entirely new branch of physics. Dr. Reed was trying to protect the old, existing structure of equations, not demolish and replace it. But the universe had a different plan. When she tested her new formula against existing experimental findings, the alignment was instantaneous and perfect. Every data curve of the black body spectrum matched, like notes in exquisite harmony. In that quiet triumph, Dr. Reed had, without intending to, sounded the first foundational note of a new age. The profound impact of this discovery lay not simply in correcting a mathematical flaw, but in what it implied about the ultimate nature of reality. If energy could only be transferred in fixed packets, then nature was not, in fact, smooth and continuous. beneath the steady flow of heat and light lay a hidden digital texture to existence, a fundamental granularity. It was as if the universe ran, not on continuous analog waves, but on a fundamental existential blueprint. Naturally, Dr. Reed did not immediately embrace the role of a revolutionary. In her presentations, she offered her findings modestly, almost as if embarrassed by their sheer strangeness. Yet, within a few short years, a generation of younger researchers would seize her concept, carrying it far beyond her original cautious intent. Her reluctant hypothesis would ignite the most profound transformation in physics since the time of Newton, a change that would redefine how we understood light, matter, and even the very concept of objective reality. Dr. Reed's discovery was also a powerful reminder of how scientific progress often occurs, not through absolute certainty, but through discomfort and persistent anomalies. She sought neat, tidy numbers, not a paradigm shift. But the measured data refused to yield until she surrendered to something radical and counterintuitive. Sometimes, the smallest step, taken with great reluctance, is the one that opens a door no one ever expected to find. To appreciate the scale of what she had discovered, try to visualize this. If you took all the thermal energy radiated by a warm object and divided it into its smallest possible pieces, each one would carry an amount proportional to Reed's constant, multiplied by the light's frequency. For light in the orange spectrum, the quantum unit would be small. For blue light, it would be proportionally larger. These packets are almost unimaginably minute. Yet every single beam of light that has ever shone, from the glow of a candle to the brilliance of a distant galaxy, is composed entirely of them. The proposition that energy existed in these discrete quanta was so alien that many established scientists resisted it for a long time. But quietly and consistently, it proved correct. Every experiment confirmed its validity. Slowly, and perhaps grudgingly, the physics community began to accept that Reed's strange, small constant was real, and that the universe, beneath its apparent smoothness, resonated to an invisible rhythm. There is a certain quiet poetry in this truth. The smallest possible action, the faintest whisper of energy, fundamentally define everything that occurs in the cosmos. A single number connects the warmth radiating from a domestic hearth to the colossal glow of distant stars. Dr. Evelyn Reed once philosophized that major new ideas in science do not ultimately triumph, because older scientists suddenly change their minds, but because a new generation of scientists grows up familiar with the concepts. She was right. Her reluctant leap of faith reshaped the world, whether she desired it or not. From that first desperate attempt to balance an equation, the quantum age quietly began, and with it came a far deeper understanding of energy, not as a continuous flow of motion, but as the universe's most perfect, smallest heartbeat. Just a few years after Dr. Evelyn Reed's reluctant unveiling, a young focused clerk working in the Capitol Archives in a city in the neutral state of Alastana was silently contemplating the nature of light. His name was Elias Vance. At the time, he was 26 years old, dedicating his long hours to reviewing technical schematics for the patent office and spending his evenings wrestling with the monumental riddles of physics that seemed to go unnoticed by others. In the year 1905, a period now revered as his Annus Mirabilis, or Miracle Year, he published a series of papers that would fundamentally change our perception of the universe. One of these papers addressed a puzzle so ordinary it felt almost beneath his genius. Why does shining light onto specific types of metal cause them to instantly release minute sparks of electricity. This phenomenon was known as the photoelectric effect. Physicists had already confirmed that when ultraviolet light was directed at a metal surface, electrons were instantaneously ejected, producing a measurable electric flow. But the observed details were strange and inconsistent with theory. Brighter light did not necessarily eject more energetic electrons. Instead, only light exceeding a specific color threshold, or more precisely, exceeding a certain frequency, could dislodge the electrons at all. No matter how intense a beam of red light became, it achieved nothing. Yet, a relatively faint beam of blue light could cause an immediate, measurable spark. Classical physics theories offered no explanation. According to the long-established wave theory of light, simply increasing the brightness should increase the total energy absorbed, and therefore increase the energy of the electrons. It failed to do so. Elias Vance, having carefully studied Dr. Reid's work, took a bold conceptual step. What if Reid's strange concept, that energy is delivered in discrete packets, applied not only to how matter released light, but to the nature of light itself? What if light was not purely a smooth, continuous wave, but was also a collection of energy quanta, tiny, indivisible particles of pure energy? He termed these fundamental units light quanta. Today, we call them photons. Each photon, Vance proposed, carried a discrete amount of energy directly proportional to its frequency. The higher the frequency, the greater the energy carried by the packet. Blue and ultraviolet light possess shorter wavelengths, which translates to a higher energy per photon. Red light, having longer wavelengths, carries less energetic photons. When a photon impacts the surface of a metal, it can only knock out an electron if it carries sufficient energy to overcome the electron's anchoring force. A very bright red light might bombard the surface with countless photons, but if each individual one lacks the necessary force, none will succeed. A single ultraviolet photon, however, carries enough punch to do the job instantaneously. This idea was revolutionary because it fundamentally shattered the comforting stability that light was exclusively a wave. For centuries, various experiments had conclusively validated light's wave-like behavior. It could bend, diffract, and interfere with itself. But Vance's paper made a radical claim. Light possesses a dual nature. It is both wave and particle. Depending on how one chooses to observe it, light can spread and ripple like fluid, or it can strike forcefully like a relentless hail of invisible projectiles. It was a proposal that unsettled many, and not everyone accepted it immediately. Even Dr. Reid herself hesitated to fully embrace the implication. Yet, experiment after experiment continued to confirm Vance's precise prediction. The energy of the electrons that were ejected depended exclusively on the light's frequency. Exactly as his equations predicted, the photoelectric effect was not only a real phenomenon, it quickly became one of the most precisely verified truths in all of modern physics. Decades later, this specific discovery would be the one to earn Elias Vance the highest accolades, though many often mistakenly assume it. Was for his work on relativity. It was, in fact, for his profound explanation of the light quanta. In the rhythm of our everyday existence, this strange behavior is all around us. Every time sunlight strikes a solar panel, photons are absorbed by the atoms on the panel's surface. Their energy instantly dislodges electrons, generating an electrical current. This is the precise principle Vance described in 1905. The light impacting the sensor of your phone's camera, the gentle glow of an LED bulb, even the activation of automated doors that utilize photosensors, all depend on the photoelectric effect. The universe, it appears, is built upon this quiet, instantaneous transaction. Photons exchanging energy with matter, minimal currency unit by minimal currency unit. Every photon is a tiny packet of currency, a coin of light minted in the immense furnace of the universe, exchanged throughout the vast marketplace of reality. Some are forged deep within the heart of burning stars. Others are generated by the lamp in your living space. But all adhere to the same non-negotiable rule. No photon can yield more or less energy than its intrinsic frequency allows. This fundamental granularity was much more than a clever mathematical fix for an experimental anomaly. It represented a profound shift in how the scientific community understood the world. Classical physics conceptualized energy as something smooth and unbounded, like a continuously flowing river. Vance showed that it could also behave like an instantaneous shower of pebbles. And yet, light never ceased to be a wave. It was somehow both identities at once. This fundamental paradox would challenge and inspire physicists for the rest of the century. How can a single entity be two mutually exclusive things simultaneously? How can a beam of light propagate like a wave but impact a surface like a particle? Vance did not claim to resolve this enigma. He simply pointed out that the experimental evidence demanded this dual interpretation. The universe, he suggested, does not owe us simplicity. It simply asks us to pay meticulous attention to what is. There is a quiet, powerful poetry in the idea. Picture a ray of sunlight gently streaming through a window pane. To your perception, it is a single, continuous, golden thread. But, in fundamental truth, it is an intricate orchestra of photons, each one vibrating at its precise frequency, each carrying an exact quantum of energy across the immense emptiness of space. They may travel together for millions of years, only to conclude their journey by striking your skin, warming it by the smallest imaginable increment. That sensation of warmth, the comforting touch of light, is the summation of countless tiny collisions, with each photon surrendering its energy to your body's atoms. Vance's light quanta forced science to accept that nature is far more mysterious and multifaceted than human intuition suggests. It blurred the traditional boundaries between energy and matter, between continuous waves and discrete particles, between the visible and the unseen. And, perhaps most intriguingly, it hinted that the universe might be built from information itself, discrete packets of energy behaving like individual notes in a cosmic score. When you truly contemplate it, every light source you have ever witnessed, every flicker of a candle, every distant star, is narrating the same story. It is a continuous stream of photons, messengers originating from somewhere else. Each one faithfully carries its precise inherent quantum of energy, unbroken and unaltered since the moment of its creation. And so, from a small, seemingly minor mystery involving a metal plate and a beam of light, Elias Vance rendered the invisible tangible. He transformed Dr. Reid's abstract quanta into something that could be empirically measured, tested, and felt. He demonstrated that light itself is both wave and particle, both continuous and discrete, both elegant and strange. A century later, the photoelectric effect continues to power a vast portion of our modern technological world. Yet, it also serves as a potent reminder that even the most familiar phenomena, like the light pouring through your window, are meticulously woven from mysteries far deeper than our immediate imagination. Light, ultimately, is not merely illumination. It is the universe communicating through energy, one precisely tailored photon at a time. After Elias Vance showed that light itself is composed of minute packets of energy, the next logical question was what this implication meant for matter. If light was quantized, did atoms too possess this fundamental granularity? In the early decades of the 20th century, atoms remained highly enigmatic, minuscule, invisible architectures that seemed to actively resist comprehensive explanation. Researchers knew that they contained electrons and a central positive nucleus, but no one understood why atoms consistently emitted light only in such precise colors, or why those electrons didn't simply spiral inward and collapse into the center, like miniature planets collapsing into a sun. It was a physicist from the Northern School of Thought named Professor Silas Croft who found a vital clue, and he did so by listening intently to the atom's unique music. Croft was young, immensely brilliant, and relentlessly curious. In 1913, while working at a research station overseas, he began a conceptual reimagining of the atom's structure. Utilizing the nascent quantum ideas that Reed and Vance had so recently revealed. He proposed a truly radical concept, that electrons could only exist in specific defined orbits around the nucleus, with each orbit corresponding to an exact, non-negotiable energy level. They could not reside in the spaces between these assigned levels. No more than a person could stand halfway up a tiered fountain without a structural ledge beneath them. In Croft's conceptualization, an electron moving within its designated orbit was completely stable. It would neither lose energy nor plummet into the nucleus. Only when it performed a jump from one fixed orbit to another did it either emit or absorb a photon, a specific packet of light energy exactly equal to the difference in energy between the two levels. The greater the separation between the levels, the higher the frequency and energy of the emitted photon. This single, elegant idea finally offered an explanation for why atoms emitted light in such sharply defined, discrete colors. If you direct the light from a glowing gas through a prism, it does not produce a continuous, seamless rainbow spectrum. Instead, it yields a fixed set of thin, bright lines, an absolute barcode of color. Every elemental substance has its own unique, recognizable pattern. Hydrogen, for instance, produces very distinct lines in the red, blue, green, and violet segments. These specific spectral lines had puzzled scientists for decades, but Croft's model immediately provided clarity. Each line unequivocally represented a specific, allowable energy jump performed by an electron within that element's atom. Every atom possessed its own internal ladder of set energy elevations, and those specific ladders were unique to every element. It was as if every single atom was playing its own prescribed tune in a universal orchestra. Each unique note was generated by an electron's sudden leap between allowable levels. The bright streaks of color you observe from burning elements are, in fact, that atomic music made visible. Croft's model was deceptively simple, yet immensely powerful. It worked flawlessly for hydrogen, the simplest atom known. Later revisions by subsequent scientists would show that the scenario was far more intricate for atoms of heavier elements, but the foundational principle remained unassailable. Energy levels were fundamentally quantized, and electrons were only permitted to occupy those specific, discrete spaces. Nature, it seemed, ultimately preferred order over potential chaos. This necessity for quantization also explained why matter possesses stability. In the old classical physics, An orbiting electron was predicted to lose energy continuously and spiral inward, resulting in the instantaneous collapse of the atom in a tiny fraction of a second. But in Croft's model, that event was structurally impossible. The lowest possible orbit was the electron's ground state. It could not fall any lower without fundamentally violating the established rules of quantization. Effectively, the universe had manufactured intrinsic safety rails right into the structure of the atom itself. Croft's concept may sound abstract, but its fingerprints are everywhere in the world around us. The specific colors we perceive, the deep red of a twilight sky, the vast blue of the ocean, the vibrant green of a leaf, all depend entirely on which photons are absorbed or emitted by the atoms and molecules involved. When an atom absorbs a photon, one of its electrons performs a jump up to a higher, more energetic level. When it subsequently releases a photon, the electron instantaneously drops back down, releasing light of a specific, defined wavelength. You observe this most clearly in the warm glow of a neon sign. When electrical energy passes through the gas within the glass tube, it vigorously energizes the neon atoms, exciting electrons to those higher orbits. As those electrons inevitably return to their original stable states, they emit light that has a specific reddish-orange hue. Change the gas to argon, krypton, or helium, and you obtain different colors, each one the unique signature of that element's quantum structure. Every illuminated sign is a public demonstration of atomic precision, a quiet concert of electrons jumping between the set notes. The same fundamental principle also explains the colors of stars. When astronomers analyze the light from a distant celestial body, passing it through a spectroscope, they find specific lines missing from the continuous spectrum. Dark bands appear where certain wavelengths have been absorbed by elements present in the star's atmosphere. These missing lines act like an elemental fingerprint, allowing scientists to definitively determine the star's composition without ever needing to travel there. We can precisely identify hydrogen, sodium, iron, and even trace amounts of rare elements. All of this information is available simply because electrons adhere absolutely to Croft's quantized rules. This is the truly astonishing part of Croft's insight. It seamlessly connects the smallest possible scales of matter to the largest possible scales of the cosmos. The exact same quantum jumps that produce the color of a small candle flame also clearly mark the light that has traveled from galaxies millions of light years away. The laws governing an atom resting in your skin are the same laws that govern the cataclysmic birth of stars. And yet, for all its profound beauty, Croft's model was also a simplification. In actual reality, electrons do not orbit the nucleus like miniature planets. They exist as standing waves, dispersed like faint clouds of probability. But Croft's core insight represented a monumental step forward. It gave scientists a precise language for articulating atomic behavior that matched every experiment with elegant precision. It also provided the world with a new form of aesthetic appreciation. The understanding that atoms possessed permitted states and forbidden zones suggested a deep, underlying harmony inherent in nature. Electrons were not free to improvise or wander arbitrarily. They could only leap between the specific notes written into their intrinsic structure. Electrons don't improvise. They only perform precise solos. Their movements, though forever invisible, literally create the color of the physical world. Croft's success inspired an entire generation of physicists to explore the strange, new, and exhilarating landscape of the quantum world. The patterns he discerned in the hydrogen spectrum served as a vital map for understanding the core building blocks of all matter. And though later, more complex theories would expand and refine his initial model, the heart of it remains fundamentally true today, just as it was in 1913. Energy is not continuous. It exists in distinct, countable amounts. Every time light flashes from a spark, every time you perceive the shifting colors on the surface of a soap bubble, you are witnessing the quiet arithmetic of quantized energy levels in action. The serene glow of a neon sign, the faint twinkle of a distant star, even the precise mechanism by which your eyes detect light, all of it depends on the precise rule that Croft set down. Electrons reside in specific, stable patterns, and light is the fundamental language they utilize to communicate. It is a humbling thought to realize that the universe, at its most foundational level, operates not on disorder, but on inherent rhythm. Every element contributes its own distinct tones and harmonics, its own subtle frequencies, to the grand composition of existence. The atoms that compose your own body are participating in this as well, their electrons forever shifting and humming, releasing minute flashes of light that are far too faint for us to detect. If you could somehow hear them, the entire cosmos would register as a vibrant symphony of vibration and constant exchange. A billion instruments playing in perfect mathematical time. And all of that began with the simple, revolutionary idea that electrons are not free to go wherever they please, but must step meticulously between their allowed energy states. From the very first spark of Reed's quantum discovery to the physical structure of atoms themselves, the universe had revealed that its foundation is constructed not from pure matter or continuous motion, but from patterns. Energy meticulously arranged in steps, like precise notes on a cosmic scale. Every atom hums a melody, and light, quite literally, is its song. By the early 1920s, the atomic conceptualization was beautiful, but still critically incomplete. Professor Silas Croft's neat, tidy orbits functioned wonderfully for the single electron of hydrogen. Yet, when scientists attempted to apply the identical model to atoms of greater complexity, the underlying mathematics began to completely unravel. Electrons consistently refused to behave like miniature planets. They seemed to exist in a manner that defied a fixed location, possessing the unsettling ability to appear both here and there, moving and not moving, all in the same instant. The classical image of a single, orbiting particle, elegant as it was, simply failed to capture their genuine, strange nature. Something far deeper and more encompassing was required. A descriptive language for matter that truly embraced its inherent strangeness rather than attempting to force it back into obsolete frameworks. In 1926, an Austrian thinker named Anya Sharma began to approach the problem from a radically different angle. Since her childhood, she had been fascinated by waves, by how the vibrations on a taut string could seamlessly form stable, standing patterns of sound. The concept that matter itself might behave like a wave had been previously introduced by Louis de Broglie, a French theorist who suggested that every particle possesses an associated wavelength, directly related to its momentum. It was a fiercely bold, counterintuitive concept. Perhaps, Sharma considered, electrons did not circle the nucleus like minute marbles, but instead flowed around it, like gentle ripples surrounding a submerged stone. She decided to take this idea absolutely seriously, and to construct the exact mathematics that could fully describe it. The resulting formulation became renowned as the Sharma equation, a deceptively simple formula that would fundamentally alter physics forever. Instead of meticulously describing electrons as pinpoint locations in space, Sharma described them as wave functions, patterns of pure probability that diffused through space like a soft, vibrating fog. The wave function did not inform you of the electron's exact location. It informed you of the location where the electron was most likely to be found. Its peaks corresponded to high probabilities, its troughs to low ones. The critical act of measurement, of observing or interacting with the electron, would cause this hazy cloud of potential to instantaneously collapse, revealing one concrete outcome from the multitude of possibilities. It was an astonishing conceptualization. The atom was not a predictable clockwork system of interlocking components, but a shimmering blur of pure probabilities. Within it, energy and matter seamlessly merged into a single, elegant dance of chance and defined structure. Where Croft's atom had posited sharp, distinct orbits, Sharma's atom possessed standing waves, continuous, elegant patterns of vibration that wrapped perfectly around the central nucleus. The allowable energy levels of the atom directly corresponded to wave patterns that fit neatly, without overlap or interruption. Just as a guitar string is constrained to vibrate only at specific, allowed frequencies, electrons could only exist in wave forms that resonated perfectly with the space surrounding the nucleus. This visual image explained why electrons could only occupy discrete energy levels. If a wave pattern did not fit the geometric constraints, it simply could not exist. Energy quantization was not arbitrary. It was the direct consequence of the wave's own geometry. Croft had accurately described the result. Sharma showed the precise underlying reason. The deep beauty of this new model resided not only in its unprecedented accuracy, but in its visual imagery. If we could somehow visually perceive the atom as Sharma did, we would not find tiny dots circling a nucleus. We would perceive shapes, vast, ghostly clouds with varying densities, each representing the mathematical probability of encountering an electron in that specific region. The simplest hydrogen atom would appear as a soft sphere of gentle mist, gradually dissipating into space. Atoms with higher energy would form exponentially more complex patterns. Dumbbell shapes, intricate clover leaves, toroidal rings. Complex geometries of possibility that resemble magnificent abstract artwork. These clouds are not static entities. They shimmer, shift, and merge as electrons transition between states. Yet the movement is not mechanical or deterministic. It is purely statistical. The atom's entire architecture is fundamentally defined by probability itself. The idea that something so concretely solid, the matter that forms your body, your desk, and the world surrounding you, could be structurally built upon intrinsic uncertainty was both thrilling and deeply unsettling. For many physicists, including Sharma herself, this probabilistic nature of reality proved immensely challenging to fully accept. She once wryly commented that she did not care for the concept of jumping electrons or randomness being woven into the fundamental laws of nature. But the experiments consistently proved her mathematics correct. Wherever scientists focused their attention, they found that the equations of wave functions predicted nature's behavior with breathtaking, minute precision. It is a profound realization to consider that the universe is constructed not from certainty, but from possibilities weighted by likelihood. Yet, paradoxically, this surrender of absolute precision endowed physics with far greater descriptive power than ever before. With the Sharma equation, scientists could accurately predict how atoms bind together to form complex molecules, how specific materials conduct electrical energy, and even how stars are able to fuse elements deep within their blazing cores. Chemistry itself became an elegant expression of wave patterns, an art of probability meticulously sculpted by energy. If you pause now and attempt to picture this world, it is hauntingly beautiful. Imagine every atom surrounding you, in the air, in the fabric of your clothes, in your very skin, as a network of shimmering clouds, each one buzzing with silent potential. The space that appears empty between the nucleus and the electron is not, in fact, empty. It is saturated with the hum of mathematical possibility. These electron clouds overlap and subtly blend, forming the chemical bonds that hold everything together. You are, quite literally, composed of probabilities that have, for the moment, chosen to coalesce into existence. In this profound way, the atom is transformed into a kind of cosmic instrument. Each allowable wave pattern corresponds to a particular energy level, a distinct pure note in the atom's song. When an electron transitions from one specific pattern to another, it either emits or absorbs a photon, a specific musical tone of light, whose frequency precisely matches the mathematical difference between the two notes. The colors that define our world, the majestic glow of the stars, and the subtle shimmer of metals all elegantly emerge from this grand resonance of waves and quanta. Sharma's theory also carried a quiet philosophical weight. It strongly suggested that nature does not delineate hard, absolute lines between things. Instead, it trades certainty for inherent elegance. Instead of defining where something is, it presents us with a rich landscape of where it could be. Reality, at its core, is fluid. Not a static arrangement of fixed objects, but a continuous vibration of potential and information. This realization changed far more than just physics. It reshaped how humanity fundamentally thinks about existence itself. Vance, the realist, famously disliked this pervasive uncertainty, grumbling that the Creator does not throw the cosmic dice. But the quantum world requires no approval. It simply is. The dice are always rolling, whether we choose to watch or not. And curiously, this cosmic randomness is not chaotic, but profoundly ordered, strictly adhering to statistical laws that make the unpredictable, in a very real sense, predictable after all. Today, the intricate shapes predicted by Sharma's precise mathematics can be beautifully visualized using modern computers, revealing a hidden architecture beneath all things. These visualizations show astonishingly intricate layers of symmetry and geometry that rival the perfect patterns found in snowflakes or seashells. Every orbital shape, every subtle fold of probability is a direct product of energy finding the most harmonious way to exist. When you observe the apparent solidity of the world around you, it is easy to forget that this structure is entirely built upon this foundational uncertainty. Yet, this very uncertainty is the condition that allows atoms to form chemical bonds, molecules to flex and twist dynamically, and life itself to adapt and thrive. A perfectly rigid, deterministic universe would be sterile and unchanging. It is the minute flickers of chance, the wave of potential beneath every single particle, that makes the universe alive with continuous creativity. So, the next time you conceptualize an atom, do not visualize small spheres whirling around a nucleus. Instead, imagine music frozen in space, standing waves of pure energy resonating in exquisite harmony. Within each and every vibration resides the ultimate possibility of light, of matter, of everything we know. And perhaps that is the quietest, most elegant truth of all. that existence is not a fixed thing, but a melody, a quantum wave endlessly resonating, meticulously shaping the patterns of reality. Beautiful, uncertain, and profoundly alive. In the strange, shimmering world of the quantum, even the simple act of observation can, fundamentally, alter what one finds. This is not merely a poetic expression. It is one of the most deep-seated discoveries in all of science. In the 1920s, a young, pioneering physicist named Kai Jensen stumbled upon a truth so unsettling that even Elias Vance found it immensely difficult to accept. Jensen demonstrated that nature imposes an absolute, fundamental limit on what can be known simultaneously about a particle. The more sharply one attempts to measure one intrinsic property of a particle, the more completely another property becomes blurred. This is famously known as the uncertainty principle. Although the word uncertainty does not entirely capture its profound scope, it does not stem from human error or from the clumsiness of our instruments. It is a fundamental property woven into the very structure of reality. Even in a theoretically perfect experiment, no amount of ingenuity can violate this core rule. If you attempt to measure an electron's exact location, you lose all definitive track of its momentum, its movement. Pin it down to a single point, and its future movement becomes unknowable. Focus precisely on how fast it moves, and its exact location blurs into a smear of possibility. It is as if nature firmly insists that absolute precision must always be paid for with mystery. Jensen's idea was completely revolutionary. Until that time, physicists had comfortably assumed that if they could only construct superior tools, they could eventually know everything about any given system, the exact location and precise movement of every particle. But the quantum world refused to cooperate with that expectation. At the minuscule quantum scales, the act of measurement itself becomes an essential part of the story. To visually perceive an electron, one must shine light upon it. But the photons used for this observation inevitably strike the electron, subtly nudging it out of its previous path. There is no means of peeking without poking. Observation and disturbance are intrinsically inseparable. This principle can be expressed in a single line of mathematics, but its conceptual meaning is far deeper than any formula. It tells us that reality is not a static picture patiently awaiting examination. It is an active, restlessly energetic dance. Every particle trembles with intrinsic uncertainty, as though reality itself jiggles too swiftly for absolute stillness. That inherent jitter, though invisible, is the perpetual engine of everything that occurs. To grasp how profound this is, imagine a perfectly balanced chime gently vibrating in absolute darkness. The precise location of the chime at any given micro-moment can never be absolutely pinned down. It is perpetually moving through a range of possibilities. That vibration is the sound. Without that continuous motion, there would be silence. In the same profound way, the universe's inability to remain absolutely still is what fundamentally gives rise to energy itself. The tremble of uncertainty is what maintains existence as alive. Jensen's uncertainty also applies to the twin concepts of time and energy. One cannot know both with perfect simultaneous accuracy. The shorter the duration one attempts to examine, the less precisely the energy of that moment can be defined. This is not a flaw in the system. It is, in a way, a written permission slip embedded in the laws of physics. For infinitesimally brief moments, energy is allowed to fluctuate, to instantaneously appear or vanish like sparks in the darkness, so long as this borrowing is repaid almost instantly to maintain the overall cosmic balance. Nature permits these tiny, short-term energy loans, provided they are settled almost immediately. These momentary fluctuations are not merely abstract concepts. They occur everywhere, constantly, even in the region we mistakenly label empty space. Virtual particles flicker into and out of existence, instantaneously borrowing energy from the fundamental void and then returning it before they can be conclusively caught. They exist for impossibly short durations, trillionths of a second. Yet, their fleeting presence leaves a measurable imprint. The weak attraction observed between two uncharged, highly polished metal plates in a vacuum, a phenomenon known as the Finch effect, arises directly from this restless sea of temporary particles. The vacuum, it turns out, is never truly empty. It is an ocean of pure potential and perpetual hidden motion. When you truly consider it, this foundational restlessness is quietly comforting. The universe is not static, rigid, or mechanical, but instead is utterly alive with activity. Even in its most quiescent moments, stillness in the absolute sense simply does not exist. Everything vibrates, everything fluctuates. Even the atoms that comprise your body tremble with quantum uncertainty. Their electrons form perpetually shifting clouds of probability. This blurring between what can and cannot be perfectly known also forces us to radically re-examine what it means to truly understand something. For many centuries, science aspired to describe the world in perfect, granular detail, to measure, predict, and control every event. Jensen's discovery gently reminds us that total microscopic control is an inherent illusion. The closer you look, the more the core reality slips subtly through your fingers. But far from being a failure, this uncertainty is a deep source of freedom and creativity. It allows for novelty, for immense complexity, and for life itself. If every particle could be pinned down precisely, if the universe were perfectly predictable in every detail, nothing genuinely new could ever occur. There would be no surprises, no spontaneity, no genuine change. The uncertainty principle guarantees that the future is not indelibly carved in stone, but instead is sculpted in subtle mist. It leaves the necessary room for the universe to genuinely breathe. Vance, ever the traditionalist, was deeply disturbed by this notion. He famously declared that the Creator does not throw the cosmic dice. But quantum mechanics responds cheerfully that not only does the Creator roll the dice are still rolling everywhere, all the time. And the astonishing truth is that this cosmic randomness does not lead to disorder. It averages out to consistently produce the stable, profoundly ordered world we readily observe. From the jittering of electrons comes the absolute solidity of matter. From chance arises stable pattern. One could accurately say that the uncertainty principle is the fundamental heartbeat of quantum energy. Those minute fluctuations, the intrinsic inability of particles to remain perfectly still, are what make phenomena like zero-point energy possible. Even at the theoretical temperature of absolute zero, when all thermal motion should have ceased, the uncertainty principle ensures that there is still a faint vibration remaining, a subtle whisper of energy that can never be entirely removed. The universe, it seems, structurally refuses to fall completely silent. This is far more than an abstract scientific finding. It is a profound philosophical statement. It implies that change is structurally built into existence. The smallest foundational building blocks of nature are restless, not by choice, but because they are physically compelled to be. Reality does not pause. It oscillates, flickers, and hums. Everything we see, every star and every atom, is an echo of that foundational tremble. And yet, rather than perceiving this as a limitation, Jensen perceived a deep beauty in it. He once wrote that what we observe is not nature in its pure state, but nature exposed to our method of questioning. In other words, the universe is a dynamic conversation, not a static photograph. Each measurement we perform is a question, and each answer depends fundamentally on how we choose to ask it. Consider how liberating that truly is. It signifies that the world is not permanently frozen in absolute certainty. It is an ever-evolving story, narrated through the immense scope of possibility. The same uncertainty that prevents us from ever knowing everything is precisely what allows things to exist at all. When you sit quietly and perceive the rhythm of your own pulse, that fundamental alternation between presence and pause is perfectly mirrored in the very foundations of physics, between every moment of existence and non-existence. The universe perpetually balances itself, trembling delicately in the space between. Reality is not a solid, fixed state. It is alive with constant motion, far too quick for our immediate perception to catch. Every field, every atom, every patch of vacuum space participates in this grand uncertainty dance, a continuous waltz of probabilities and possibilities, spinning eternally in the light of existence. And in that fundamental motion, in that shimmering imperfection, lies the most remarkable truth of all. Perfection is not defined by stillness. It is defined by movement. The universe does not require certainty to be beautiful, only balance. By the time physicists had grown conceptually comfortable with electrons behaving as waves of pure probability, another monumental question inevitably emerged. Waves in what? If particles possessed the capacity to behave like ripples, then there had to be something that was rippling. The idea of matter existing as both wave and particle was astonishing enough, but it represented only half of the story. Beneath the shimmering clouds of probability lay something far deeper, something that would ultimately redefine the very meaning of matter and energy. This transition was the genesis of the quantum field revolution, a paradigm shift so profound that it quietly rewrote the foundational tenets of reality itself. The initial hint came from an old, familiar phenomenon, the electromagnetic field. Long before the quantum era, scientists had conclusively shown that both electric and magnetic forces could be perfectly described as invisible fields permeating all of space. Move an electrically charged particle, and the field instantaneously changes. Disturb it, and waves of electromagnetic energy ripple outward at the fixed speed of light. These very ripples are precisely what we perceive and define as light itself. When the new quantum model arrived, physicists realized something extraordinary. Those waves were not purely abstract concepts. They were structurally composed of photons, each one an indivisible packet of energy. It did not take long for this logic to be universally expanded. If light originated from oscillations within the electromagnetic field, perhaps everything in existence originated from similar underlying fields. Every fundamental particle, the electron, the proton, the quark, and beyond, might be nothing more than a localized ripple within its own distinct, invisible sea. Instead of picturing particles moving through space like solid billiard balls, the ultimate reality was an ocean of fields, each intrinsically capable of producing the precise ripples that we identify as particles. Imagine the universe as a massive, overlapping assembly of invisible, interlinked oceans. There is the electron field, the photon field, the quark field, the gluon field, the Higgs field, and dozens more, all interwoven and continuous, utterly filling every single corner of space. They are not entities floating in space. They are space. Empty air, the vacuum between galaxies, the minuscule gap between your hands, all of it is thick with these unseen fields, perpetually humming quietly with potential. When one of these fields becomes locally excited, say a minute pulse travels through the electron field, we subsequently detect that excitation as an electron. That is correct. An electron is not a little solid speck. It is a vibration, a highly localized ripple in an ever-present field that fundamentally extends across the entire universe. Remove that specific ripple, and the underlying field remains, calm, stable, and eternally ready to vibrate again. It is a truly radical concept, yet the mathematics leaves absolutely no room for doubt. Fields are the fundamental structural ingredients of reality. Particles are merely the temporary disturbances, the precise excitations that momentarily arise and fade like waves on the surface of a pond. Even a single atom is, in this view, a collection of synchronized vibrations, a miniature symphony of interacting fields. The photon, the particle of light, is a ripple within the electromagnetic field. The electron is a ripple in the electron field. Quarks, the building blocks of neutrons and protons, are ripples in their respective quark fields. When these various fields interact, energy is instantaneously transferred from one to another. A photon interacts with the electron field to generate light. A gluon mediates the intricate dance between the quarks inside an atomic nucleus. Every physical event, every spark, every collision, every pulse of a heartbeat, is a complex exchange of energy occurring between these invisible foundational seas. In this contemporary view, the universe is less like a vast collection of fixed objects, and far more like a grand, perpetually vibrating fabric. The familiar, intuitive idea of matter as solid stuff gives way to something far more elegant: patterns of movement. What we perceive as stable and permanent is, in fact, the complex play of these fields, with the waves only appearing stable due to the regularity of their rhythm. Consider the Higgs field, for instance. It permeates the entirety of space. And when certain particles interact with it, they acquire what we call mass. This does not happen because the field physically weighs them down, but because it subtly resists their motion in a specific, measurable way. Without this pervasive field, there would be no stable atoms, no planets, no living beings. Everything would zip through the cosmos at the speed of light, unable to slow down or clump together. You could say that the Higgs field gives the universe its essential substance, not by adding physical matter, but by shaping how the particles move through its quiet, constant resistance. To truly visualize this structure, close your eyes and imagine overlapping, intricate oceans, each one infinite, invisible, and utterly alive with gentle, ceaseless motion. Where they ripple, they spontaneously give birth to the physical world. Where they precisely intersect, forces instantly arise. Where they stabilize, matter is able to take form. Even in the profound emptiness of intergalactic space, where no atoms drift and no light is passing, these fields persist. They cannot be switched off or removed. Space itself is never truly empty. It is the calm, expansive surface of a deep and endlessly restless sea. This realization completely turned physics inside out. Instead of continuing to ask what the universe is structurally made of, scientists began asking how it fundamentally behaves. The core question shifted from what is a particle to what does the field look like when it moves. Every experiment in modern particle physics, from the smallest laboratory setup to the colossal collisions inside the Ethereum Institute, is fundamentally a method of poking these fields and meticulously observing the ripples they produce. When physicists first detected the Higgs boson particle in 2012, they were not so much discovering a new, isolated particle as they were definitively confirming the actual existence of the Higgs field itself, catching one fleeting wave crest in an ocean that had always been subtly present. It is a truly humbling thought. The apparent solidity of your chair, the warm light from your lamp, even the atoms that compose your physical body. These are not separate, isolated entities floating in a void. They are merely different vibrations of the same universal fabric. You are, quite literally, a pattern in motion, a fleeting, complex arrangement of ripples within a cosmic, continuous sea. In this powerful light, the age-old philosophical debate concerning matter versus energy begins to completely dissolve. They are not two distinct, separate things at all, but rather two descriptive faces of the same underlying phenomenon. Fields are energy that has been meticulously structured by rules and specific symmetries that ultimately give rise to the immense diversity of the universe. When those fields ripple, we observe particles. When they appear to rest, we label it empty space. And yet, even rest is an illusion. According to quantum theory, a field can never be perfectly, absolutely still. The uncertainty principle guarantees a faint, residual vibration even in the total absence of particles. A stable, low-level baseline hum known as zero-point energy. It is as if the universe cannot tolerate absolute silence. Even in perfect darkness, something is always moving. Quantum field theory, the intellectual framework that successfully unites all these concepts, is arguably the most profoundly successful theory in all of science. It accurately predicts the behavior of particles to astonishing levels of precision, sometimes extending to more than 10 decimal places. And yet, it possesses a strange serenity, an almost spiritual elegance. It suggests that the entire universe, from the largest galaxies to the smallest atoms, elegantly emerges from a single, continuous fabric of fields, which are endlessly weaving and unweaving themselves. When you begin to conceptually picture the world in this manner, the traditional meanings of solidity and emptiness completely lose their original meaning. Every star, every surface, every breath you draw is a ripple in something far larger, invisible, and intrinsically connected. There is no true, fundamental separation, only patterns interacting across an immense ocean of potential. Matter, therefore, is not constructed from stuff. Matter is fundamentally constructed from structure, from rhythm and resonance, from motion sustained in the darkness. The universe is less like a rigid machine and far more like a delicate melody played in the precise language of fields. And so, when you look down at your hand, or observe a falling leaf, or perceive the distant shimmer of starlight, what you are truly witnessing is the same thing expressed in countless different forms. The quiet, ceaseless motion of invisible oceans overlapping and interacting through everything. Matter is not made of things. Matter is made of motion. Matter is not constructed from stuff, but from patterns moving in the dark. If you could somehow completely strip the universe of every single star, planet, dust cloud, and atom. If you could successfully remove every last photon of light and every minute whisper of heat, one might intuitively believe that what would remain is absolute nothingness, a silent, featureless void. But quantum physics insists on narrating a fundamentally different story. In the quantum model, even the deepest vacuum is not truly empty. It is saturated with activity, a restless sea of invisible motion. Beneath the calm, expansive surface of space lies a constant, minute shimmer of creation and annihilation, a whisper of energy that can never be entirely silenced. This pervasive background hum of existence is correctly termed zero-point energy. It is the absolute lowest possible energy state a system can sustain. It is the fundamental ground note of the universe, the minimal energy that stubbornly remains even when everything else has been meticulously taken away. Classical physics postulated that if one cooled an object sufficiently, all motion could be stopped entirely. But quantum theory definitively states otherwise. Even at the theoretical temperature of absolute zero, when all thermal energy is absent, the underlying particles and fields continue to subtly quiver with minute vibrations. The universe, it seems, is fundamentally incapable of absolute stillness. These minuscule fluctuations originate directly from the uncertainty principle itself. Recall that both a particle's position and its momentum can never be known with perfect precision simultaneously. If a quantum field were perfectly motionless, its energy and its rate of change would both be exactly defined, a condition that quantum mechanics explicitly forbids. Therefore, the field must perpetually retain a minimal amount of motion, a persistent uncertainty. It wobbles, even in what appears to be pure nothingness, and that perpetual wobble inherently imbues the vacuum with its faint, yet measurable, irreducible energy. To conceptually visualize it, imagine attempting to calm a large bowl of liquid gelatin until every single ripple has completely disappeared. You may wait for an extended period, but even the smallest residual vibration, a distant sound wave, a subtle whisper of gravity, will inevitably stir it again. The physical vacuum of space behaves in precisely the same manner. It quivers with microscopic ripples of energy that can never be fully and completely smoothed out. These subtle ripples have real, quantifiable, measurable effects. Quantum fields are continually generating pairs of virtual particles, minute flashes of matter and antimatter that appear, borrow a small fraction of energy, and then vanish again almost instantaneously. They are labeled virtual because they do not persist long enough to stabilize into real permanent particles. But for their fleeting instant of existence, they actively influence the world around them. They exert subtle tugs on adjacent atoms, shift the precise paths of electrons, and even influence the fundamental forces operating between objects. One of the most striking experimental proofs of this invisible, ceaseless motion was established in the 1940s by a researcher named Dr. Alistair Finch. He conceptually imagined placing two perfectly smooth, uncharged metal plates extremely close together, separated by only a few billionths of a meter, and then considered the theoretical outcome. According to established classical logic, nothing should occur. After all, the plates possess no charge, and the vacuum between them is supposedly empty. But Dr. Finch's precise quantum calculations predicted a different outcome. The quantum fluctuations in the vacuum would behave differently between the plates than they would in the vast space outside them. Only specific longer wavelengths of virtual energy could geometrically fit within that exceptionally narrow gap, which meant there would be marginally less vacuum energy inside the gap than outside. The unexpected result: the plates would be pushed together, not by any mechanical force, but by the subtle external pressure of empty space itself. This phenomenon became known as the Finch effect, one of the most compelling demonstrations that nothing is, in fact, far from empty. Subsequent experiments confirmed Finch's precise prediction with remarkable accuracy. Even within the quietest vacuum human technology can achieve, the underlying quantum activity pushes back. It is almost paradoxical, the very concept of emptiness exerting a measurable physical force. And yet, once one understands that the vacuum is not merely absence, but active presence, the paradox completely dissolves. The fields that ubiquitously fill all of space are never truly at rest. Their endless, subtle fluctuations signify that the universe, at its absolute foundation, is far more like a simmering pot than a still, placid pond. Zero-point energy is far more than just a scientific curiosity. It touches upon some of the deepest, most complex mysteries in modern cosmology. When astronomers observe distant galaxies, they note that the expansion of the entire universe is inexplicably accelerating, as if some unseen force is gently pressing the cosmic accelerator pedal, driving everything further apart. They term this mysterious phenomenon dark energy. No one currently knows its precise nature, but one leading hypothesis is that it could be the energy of the vacuum itself, the collective, accumulated effect of all those minute, microscopic quantum fluctuations. If this proves true, then the very fabric of space is inherently infused with an energy so vast and diffuse that it ultimately shapes the fate of the entire cosmos. Here lies the most astonishing part of the whole scenario. When physicists meticulously attempt to calculate the theoretical amount of zero-point energy that should exist in empty space, the resulting numbers are unbelievably immense, far exceeding what every single observation allows. In fact, the predicted theoretical value diverges from the observed, actual value by an almost unimaginable factor, sometimes described as the number 1 followed by 120 zeros. That astronomical number represents the largest, most embarrassing mismatch between scientific theory and experiment in the history of science. It strongly suggests that something profound is currently missing from our comprehensive understanding of how the vacuum fundamentally behaves. The universe appears to hold just enough of this invisible energy to sustain its expansion slowly, gracefully, and gently, instead of violently tearing itself apart in an instant. It is as if the cosmos has meticulously tuned itself with exquisite precision, perfectly balancing on the knife's edge between explosion and absolute stillness, choosing harmony over chaos. Even so, the fundamental principle holds firm. There is no true void. The vacuum consistently hums with fluctuations, borrowing and instantly repaying energy on timescales too fast and spatial scales too small for any direct human observation. These ephemeral, fleeting processes underpin absolutely everything, from the forces binding atoms together to the fundamental stability of matter itself. Without them, the world as we intuitively know it could not physically exist. In a profound way, the vacuum's intrinsic restlessness perfectly mirrors the balance between chaos and order that defines nature at every conceptual level. Just as the seemingly placid surface of the ocean conceals countless unseen, powerful currents, the apparent calm of empty space conceals ceaseless, powerful motion. Every single atom, every photon is built upon this pervasive background hum. The universe's quiet moments are not silent. They are completely filled with the faint, steady vibration of possibility. If you could somehow listen to that fundamental vibration, not with your ears, but with a sense specifically tuned to energy, you might perceive a faint, omnipresent murmur. Not a sound in the traditional sense, but a steady rhythm, a cosmic pulse that has been playing continuously since the very beginning of time. That quiet hum is the zero-point energy of the vacuum, a icy, relentless reminder that nothingness itself is fertile ground. It fundamentally contains the seeds of everything that has ever existed or ever will exist. Philosophically, this radically reshapes the ancient notion of nothing. In common, everyday language, nothing implies absence, the total lack of anything at all. But in physics, nothing is an active participant. It is a dynamic stage that perpetually vibrates with hidden, immense energy, utterly ready to spontaneously create particles at a moment's notice. When we hypothesize that the universe sprang from nothing, perhaps we truly mean it sprang from this restless vacuum, a nothing that was already actively humming with potential. It is humbling to realize that even the immense emptiness between galaxies is not truly empty. Every single cubic centimeter of space, no matter how dark or desolate it appears, holds this pervasive background of energy. It is the ultimate paradox. The quieter the universe seems to be, the more intensely alive it becomes. You can conceptualize zero-point energy as the softest possible whisper of existence. It does not construct atoms or radiate visible light. It simply is. It ubiquitously fills every corner of the cosmos with a baseline vibration, a persistent reminder that fundamental reality never truly switches off. And from this quiet, trembling foundation, everything else elegantly emerges. Matter, light, stars, and even consciousness. Space itself stretches, powered by its own hidden energy. Whenever a groundbreaking scientific discovery truly captures the collective imagination, powerful myths and speculation are never far behind. The concept of quantum energy, those continuous, minute ripples in empty space, has served as a deep inspiration, not only for physicists, but also for writers, inventors, and, inevitably, the occasional conspiracy theorist. After all, if even the perfect vacuum of space is absolutely brimming with fundamental energy, surely that implies limitless power waiting to be effortlessly tapped. The thought is intoxicating. An infinite, clean energy source effortlessly drawn from nothing itself, capable of fueling vast cities, eliminating scarcity, and completely liberating humanity from its reliance on finite resources. It sounds noble, poetic, and entirely too good to be true. The widespread misunderstanding often begins with a kernel of genuine science. As we have previously explored, the quantum vacuum is definitively not empty. It is saturated with zero-point energy, a ceaseless, pervasive background hum that can never be entirely neutralized. Measurements and precise experiments unequivocally confirm its physical presence in subtle, measurable ways, through effects like the Finch force and the fundamental stability of atoms. Thus, it is unsurprising that the human imagination readily leaps from this observation to the notion of actively harnessing that energy, of simply dipping a cup into the infinite sea of the vacuum. If this energy is truly everywhere, why can't we effectively use it? The simple and often frustrating answer is that the fundamental laws of nature do not permit it. Quantum mechanics may structurally grant a restless vacuum, but it also rigorously enforces cosmic balance with ruthless precision. The zero-point energy of space is a fundamental baseline, the absolute lowest possible energy level that the universe structurally permits. One cannot construct a mechanical device that successfully extracts useful work from it. This is fundamentally the same reason one cannot construct a water wheel that successfully turns in a perfectly calm, still pond. There is no net flow to harness. There is no difference, no gradient, and without a difference in energy potential, there is absolutely nothing to drive physical motion. In the established laws of physics, this constraint is known as the conservation of energy, one of the most reliable and consistently verified principles ever discovered. Energy can neither be created nor destroyed. It can only change its form. The persuasive dream of extracting infinite free power from the quantum vacuum would fundamentally require violating that core rule. It would necessitate drawing more energy out of the system than was put in, effectively getting something for nothing. And the universe, elegant though it is, does not issue freebies. To conceptually understand why, think of zero-point energy as the ground floor of reality's architectural building. It is the lowest possible level that can be reached. One can only ever extract useful, measurable work by operating downhill, by moving from a higher energy potential level to a lower one, much like water flowing through a turbine. But zero-point energy is the very basement, the bottom of the cosmic well. One cannot physically dig beneath it to access lower levels. Every single known process fundamentally depends on the existence of differences between high and low energy states, hot and cold, electrically charged and uncharged, moving and still. The quantum vacuum, for all its shimmering beauty, possesses no such contrast. It is in perfect, stable equilibrium. And that perfect balance is precisely the reason why everything else is able to stably exist upon it. Still, the alluring idea persists, and perhaps it always will. There is a deep, abiding romance in the notion of hidden, limitless energy, an echo of humanity's eternal, hopeful wish to utterly transcend all physical limitation. It is manifested in countless historical forms: alchemists' dreams, the philosopher's stone, perpetual motion machines, mysterious etheric forces, and now the hypothetical zero-point generator. Each generation rediscovers the beautiful dream, clothes it in the contemporary language of its time, and hopes that perhaps this time the fundamental laws will finally bend. And yet, those very laws are precisely what grant the universe its stability and coherence. Without the rigid conservation principle, without definitive limits, there would be absolute chaos. If energy could spontaneously appear from nowhere, the delicate balances that cause stars to shine and atoms to remain stable would instantly collapse. Physics would lose its fundamental poetry, because everything would become entirely arbitrary. The constancy of natural laws, those quiet, absolute boundaries around possibility, are what render the universe intelligible, beautiful, and livable. This is not to suggest that humanity has not previously harnessed extraordinary sources of energy. The sun itself operates entirely on quantum principles. Nuclear fusion, made possible by the strange, unpredictable dance of tunneling particles and quantum probability, converts mass into light with breathtaking efficiency. And even that colossal process is rigorously constrained by physics. It adheres to the rules perfectly, wasting nothing, creating stability where total chaos might otherwise have reigned. Quantum energy is not an infinite power source waiting to be unleashed. It is the steady hum that maintains the cosmos in absolute harmony. Some modern discussions of zero-point energy in popular culture often blur this line, using the phrase as a generic synonym for a limitless energy source or a mystical force. You will encounter the term in speculative films, science articles, and radio shows discussing hidden technologies. It is a captivating idea. How could it not be? But it is not what quantum physics actually describes. The zero-point energy of space is an intrinsic property of the fields themselves, not a finite resource that can be actively mined. It is part of the structure, not a potential prize waiting to be collected. Even physicists, when they first encountered the potential immensity of vacuum energy in their mathematical equations, were deeply startled by its implications. Calculations suggested that if one could somehow release even a fraction of it, the resulting amount would be staggering. But that is the crucial trick. It cannot be released. It is not stored energy. It is intrinsic energy. It is not potential power patiently waiting to be used. It is the baseline upon which all power fundamentally depends. In a profound way, it is a comforting thought that we cannot exploit it. The vacuum's untouchable energy implies that the universe remains stable. If we could drain it, we might inadvertently unravel existence itself. The very hum that superficially seems like wasted potential is precisely what holds everything stably in place. When you contemplate it from this perspective, the grand dream of infinite energy extraction feels less like a promise and far more like a fundamental misunderstanding of cosmic beauty. The laws of physics do not deny us wonder. They actively create it. They are the very reason why the world can be logically understood, why energy flows predictably, why matter coheres into stable forms. If you hold a glass of water and allow it to rest on a table, gravity pulls it downward, and the table resists with an equal opposing force. Nothing happens because the forces are in perfect balance. The vacuum's energy is functionally identical to that, a state of perfect equilibrium. To extract useful work, one would be required to unbalance it. But the instant you attempt to tilt the scales, the universe pushes back. Every attempt to violate the constraints only conclusively proves how exquisitely finely tuned they already are. There is a quiet, powerful dignity in those constraints. They inform us that even in a universe bursting with total energy, not all of it is available for us to command. The established boundaries of possibility are not obstacles. They are, in fact, the architecture of existence. They are what make life physically possible, and they give meaning to human effort. So, while the idea of limitless, free quantum power is profoundly appealing, it is the limits themselves that render the real story truly extraordinary. We can admire the quiet hum of zero-point energy, feel deep awe at its pervasive presence, and yet still respect the cosmic balance that places it firmly beyond our immediate reach. Ultimately, that is perhaps the most beautiful lesson quantum physics gently offers. That wonder does not depend upon fantasy. The truth is already strange enough, vast enough, and miraculous enough. We do not need to break the rules of nature to feel absolutely amazed by the world. The rules themselves are astonishing. Reality, with all its boundaries and necessary constraints, is not disappointing. It is believable, and it is in that very believability that its quiet, enduring beauty truly resides. Reality's constraints make its beauty believable. For the vast majority of human history, matter and energy appeared to be two completely different, separate things. Matter was solid, tangible, the physical stuff you could directly touch and feel. Energy was motion, light, or heat, something you could sense but never physically contain. But in the early years of the 20th century, Elias Vance revealed that this long-held distinction was a profound illusion. He conclusively demonstrated that matter is energy condensed and firmly confined into a stable, enduring form. This was one of the simplest and most profound revelations in science, elegantly captured in a short, deceptively gentle equation. That small relationship, energy equals mass multiplied by the speed of light squared, informs us that mass and energy are two intrinsically linked sides of the same coin. You can conceptually think of mass as simply energy that has slowed down sufficiently to become tangible. The speed of light squared is the gargantuan conversion factor, a powerful reminder of just how much immense energy is structurally locked within even the smallest quantity of matter. A single gram of material, roughly equivalent to the weight of a paperclip, potentially holds enough stored energy to fully power a major city for days, if that energy could all be released instantaneously. It is important to recall that Vance did not begin his work with cosmic theories or the concept of explosions. He began with the fundamental principle of relativity, the idea that the physical laws of nature must remain identical for all observers, regardless of their state of motion. From this single premise, he realized that energy and mass must be fundamentally interconnected. An object that is moving gains energy, and therefore, by definition, simultaneously gains a minuscule amount of mass. Conversely, if it loses energy, its mass must proportionally decrease. The two properties are structurally inseparable. Energy possesses the capacity to take the form of matter, and matter possesses the capacity to melt directly back into pure energy. At a surface level, this might sound purely abstract, but nature demonstrates this transformation every single day. Deep within the sun's scorching core, hydrogen atoms are crushed together to form helium, and in the precise process of that fusion, a small, minuscule portion of their original mass entirely vanishes. It does not disappear into nothingness. It is instantly transformed into light and heat, streaming outward across space to gently warm the planets. The energy we feel from sunlight is, quite literally, the lost mass of hydrogen, transformed into radiant energy. This process also operates in the exact reverse. Energy possesses the capacity to condense into matter, given the precise conditions. When two photons, particles of pure light, violently collide with sufficient energy, they can spontaneously give birth to a pair of particles, an electron and its identical twin, the positron, antimatter. This is termed pair creation. It is as if the energy of light becomes so incredibly intense that it curls in on itself, solidifying into stable matter. The electron and positron spin away from one another, perfect mirror images constructed from nothing but energy. But this material existence is temporary. When those two particles inevitably meet again, they instantaneously annihilate each other, releasing the precise, exact amount of energy they borrowed from the photons in the first place. In that silent instant, matter dissolves directly back into light. Creation and destruction, material and immaterial, all are structural components of the same continuous, elegant cycle. It is almost poetic how perfectly symmetrical the entire process is. The universe acts as a meticulous accountant, maintaining its books in perfect, absolute balance. No energy is ever genuinely lost. It only ever changes its inherent form, flowing between existence and non-existence like a perpetual tide. This essential balance is the structural precondition that allows stars to consistently burn, atoms to maintain their stability, and galaxies to majestically glow. When you reach out and touch a solid object, for instance, a stone or a piece of metal, it feels permanent, solid, and utterly unmoving. Yet, if you could look deeply enough inside, you would perceive that its apparent solidity is simply energy holding its breath. The particles comprising that object are in constant, high-speed motion, vibrating, exchanging photons, and being bound together by powerful electromagnetic energy. The matter you touch is genuinely just energy in a tightly bound configuration, stable yet profoundly restless at the smallest possible scales. This critical realization fundamentally changes how we perceive everything. The traditional boundary between what is and what happens begins to completely blur. A vast mountain range, a simple beam of light, a single breath of air, they are all distinct manifestations of the same universal currency, energy. Matter is merely energy that has been meticulously captured and given structure by the immutable quantum rules. The concept of converting energy into matter and back again might sound like the stuff of science fiction, but it is occurring everywhere, constantly, all the time. Cosmic rays striking Earth's upper atmosphere generate bursts of particle pairs from pure energy. Inside particle accelerators, scientists deliberately recreate these processes at will, smashing high-energy photons together to briefly conjure new particles into existence. Each creation and subsequent annihilation narrates the identical story. The dance of energy and specific form is endlessly repeating, a cycle running since the very dawn of time. Even the universe itself appears to have been born from this singular principle. In the beginning, moments after the cosmic ignition, everything that would eventually become stars, planets, and people existed as pure energy, a glowing, scorching plasma of light and motion. As the cosmos expanded and steadily cooled, energy condensed into matter, forming the first stable particles, the first atoms, and subsequently, the first galaxies. One could accurately claim that all of existence is light, slowed down and meticulously shaped by the quantum fabric of reality. If that sounds mystical, it is only because it is so fundamentally true. The chair you are sitting on, the screen you are reading, and the air you quietly breathe are all composed of energy that has been caught in the complex gravitational and electromagnetic choreography of the universe. Matter is not the opposite of energy. It is energy in an elaborate costume. This perspective also precisely explains why such vast amounts of energy can be released when matter is fundamentally rearranged or destroyed. In nuclear reactions, both fusion in stars and fission in reactors, minuscule differences in mass translate to enormous amounts of energy. This is because the conversion factor in Vance's equation involves the speed of light squared, a number so colossal that even a tiny amount of mass translates to genuinely staggering energy potential. When atoms split or fuse, the bonds holding them together rearrange, and that difference in binding energy manifests as intense light and heat. But while it is tempting to view this as a source of endless power, the same conservation laws apply rigorously here as well. The universe yields energy only in precise exchange for a structural change, never for free. For every transformation, there is an exactly equal and opposite cost. The true grandeur of EMC is not found in its potential for immense power, but in its grace. The profound symmetry of how mass and energy mutually sustain one another. You might imagine the cosmos as a colossal sculpture, constructed entirely from frozen light. An enduring work of art meticulously carved by the laws of quantum mechanics. The atoms that make up your body were once pure energy released from ancient, long-dead stars. That same energy, billions of years from now, may find a new form as some other pattern, another heartbeat in the relentless cosmic rhythm. There is a quiet, powerful reassurance in knowing that nothing truly vanishes. Even when colossal stars collapse, when matter burns away, or when you let go of something deeply precious, the energy that composed it remains. It changes, it travels, and it adopts new shapes. But it never ceases to be part of the great universal cycle. At its core, Vance's revelation was not solely about equations. It was a potent reminder that the universe is fundamentally unified, that all the dazzling variety we observe is intricately woven from the same luminous thread. Matter and energy are not separate realms, but two essential faces of the same infinite coin. So, the next time you perceive sunlight streaming through a window, remember that light is fundamentally kin to every atom in your body. It is the same foundational essence, vibrating at a different tempo. The universe, from the smallest grain of sand to the brightest star, is a continuous, self-sustaining exchange of energy becoming matter, and matter inevitably returning to energy. Solidity is simply energy holding its breath. A fleeting moment of stillness in the eternal dance of transformation. In the intuitive, everyday world, physical barriers are absolute. A solid wall absolutely stops a moving ball. A stable table rigidly holds a cup, and a securely locked door remains shut unless actively opened. But in the quantum world, the rules are far more nuanced, or, depending on your perspective, far more mischievous. At that level, particles occasionally slip through barriers that they should, by every classical definition, never be able to penetrate. They do not violently crash through or physically break down the obstacle. They simply appear on the opposite side, as if the structural obstacle were only half real. This strange, counterintuitive behavior is termed quantum tunneling, and it is one of the most essential, yet least intuitive phenomena in all of physics. Without its constant operation, the sun would not ignite, modern electronics would completely fail, and the universe itself might possess a dramatically different appearance. It is the quiet art of defying the impossible, not through brute force, but through pure statistical probability. To truly grasp tunneling, imagine a small object rolling toward a massive hill. In the classical, macroscopic world, if the object does not possess enough kinetic energy to physically climb over the top, it simply rolls back down. There is no middle ground. It either has sufficient energy or it does not. But in the quantum world, the object is not a solid entity. It is a wave, a diffuse, spread-out cloud of probability describing where it might be located. When that wave encounters a physical barrier, a portion of it reflects back, but a discernible other portion seeps through the obstacle, like a faint, vanishing echo on the far side. This is not magic or theoretical teleportation. It is the precise mathematics of wave mechanics. The quantum wave does not stop abruptly at the wall. It fades gradually, and within that fading pattern, there is always a tiny, non-zero chance that the wave continues its existence beyond the barrier. If you wait for a long enough duration, you might discover that the particle has, in fact, tunneled through. The thicker or higher the barrier, the smaller the probability, but the chance is never absolute zero. At the quantum scale, even walls possess a soft-hearted side. It is a marvelous thought, truly. Nature allows for a marginal amount of flexibility, a subtle forgiveness in its constraints. What appears utterly impossible from a traditional perspective becomes merely highly improbable from a quantum perspective. And in a universe entirely constructed from probabilities, improbabilities occur continually. One of the most spectacular, large-scale examples of tunneling occurs deep within the hearts of stars. In the core of a star like the Sun, hydrogen nuclei, which are protons, are perpetually attempting to fuse together to create helium. But there is a colossal problem. Every proton carries a positive electric charge, and like all similar charges, they violently repel one another with fierce determination. To get close enough to fuse, they must overcome an immense barrier of electrostatic force. The temperatures within the Sun, though astronomical, are not quite high enough to force that fusion using brute classical strength alone. Yet, fusion happens constantly, billions of times every single second. How? Because of quantum tunneling. The quantum probability waves of the protons overlap, and occasionally, a proton's wave leaks through the towering energy barrier. The particle borrows just enough probability to spontaneously find itself on the opposite side, where it can finally fuse with its partner. Without this fundamental loophole in nature's rules, the Sun would remain dark, and life would never have begun. Every single ray of sunlight that gently touches your face is a quiet, profound testament to quantum tunneling at work. The same principle explains another mysterious process: alpha decay. This is the manner in which some heavier, unstable atoms naturally shed particles over time. Inside the nucleus of an unstable atom, clusters of neutrons and protons, termed alpha particles, sometimes find themselves trapped by the strong nuclear force. They do not possess enough energy to escape, at least not according to classical expectations. But their quantum wave function extends just beyond the precise boundary of the nucleus. And every so often, a portion of that wave successfully makes it through. When this occurs, the alpha particle instantaneously appears outside, carrying measurable energy with it. It is as if the nucleus occasionally sighs, letting go of a tiny piece of itself through sheer quantum chance. Tunneling is not restricted to the realm of stars and nuclei. It is intricately woven into the very technology of our everyday lives. The entire modern world runs on semiconductors, the delicate, complex materials that form the heart of all computers and smartphones. Inside these materials, electrons are moving through barriers that should, by classical physics, stop them completely. Quantum tunneling permits them to flow through specific regions, creating the precise, controlled behavior that engineers design into modern transistors and diodes. The fundamental reason you are able to listen to music, read this very sentence, or send a message halfway around the world is that electrons at the smallest scales are utterly unbothered by human definitions of what is impossible. There is even a sophisticated type of imaging device, the scanning tunneling microscope, that utilizes this effect to sense the positions of individual atoms. A microscopically sharp metal tip hovers just above a surface, and electrons tunnel between the tip and the atoms directly below. By meticulously measuring that current flow, scientists can map the surface with astonishing precision, revealing not only molecules, but the patterns of their quantum states. This device, which allows us to perceive the invisible, operates solely because particles are able to quietly slip through through impenetrable barriers. When tunneling was first proposed, even highly experienced physicists found it conceptually difficult to believe. The idea seemed fundamentally absurd. How could something possibly cross a gap without actively going over it or around it? But experiments quickly and consistently confirmed its existence. Quantum particles do not rigidly adhere to the binary logic of yes or no. They exist in the in-between, strictly guided by probabilities that can never quite diminish to zero. The world, it turns out, is not structurally built from absolute certainties. It is built from chances. That might sound unsettlingly chaotic, but it is precisely the opposite. Quantum tunneling is not a violation of nature's laws. It is a direct and logical consequence of them. The rules of wave mechanics predict its occurrence perfectly. It happens not in spite of order, but precisely because of it. The universe allows for a minute amount of randomness at the smallest scales, and out of that precise randomness comes the creation of stars, complex chemistry, and life itself. There is a deeply quiet poetry in this truth. The same exact principle that powers the immense engine of our sun also powers the tiny chip in our electronics. The same rule that permits light to escape from the heart of atoms also illuminates the modern world. Every instance of tunneling, from the atomic to the astronomical, narrates the same profound story. That possibility is never fully extinguished. It is easy to categorize tunneling as abstract or strange, but it reflects something deeply natural. The fundamental idea that even boundaries possess texture. In the quantum world, barriers function more like flexible membranes than rigid walls, soft enough for possibility to subtly seep through. If particles have the structural capacity to tunnel through energy barriers, perhaps it is not surprising that stars can burn for countless billions of years, and that life, constructed from improbable chemistry, can persistently endure against all odds. When you broaden your perspective and think of it in this manner, tunneling becomes less of a scientific curiosity and far more of a quiet act of generosity from the universe. It is nature's way of silently granting permission. You may pass, even when conventional reason insists that you should not. And it is through this very act, this improbable crossing of invisible walls, that the cosmos successfully powers itself. The energy of stars, the creation of elements, the light that reaches us across the void, all of it fundamentally depends on tunneling. It is a quiet reminder that sometimes even the smallest possibility is abundantly enough. At the quantum scale, even walls have a soft-hearted side, and through that subtle softness, the universe meticulously maintains its fires. At the fiery heart of every star, far beneath its brilliantly glowing surface, a quiet miracle is occurring. One that depends entirely on the strange generosity of quantum physics. Deep within those cores, subjected to immense temperatures and pressures far beyond human imagination, atoms are engaged in a perpetual struggle between repulsion and attraction. Every single atomic nucleus carries a positive electric charge, and, like all positive charges, they fiercely push each other away with relentless determination. By every law of traditional classical physics, they should never achieve the proximity close enough to fuse. And yet, somehow, they consistently do. This deep paradox lies at the absolute center of creation itself. Every glimmering point of light visible in the night sky, every morning sunrise that brings warmth to the earth, every flicker of life that fundamentally depends on that warmth, all of it exists due to a delicate quantum trick called tunneling. Inside the core of a star, such as our Sun, hydrogen atoms are compressed together under almost unbearable pressure. The temperature there reaches approximately 15 million degrees Celsius, a heat level sufficient for the atoms to move at phenomenal speeds. Nevertheless, their mutual electrical repulsion should still keep them rigidly separated. The sheer kinetic energy they possess is simply not quite enough to overcome the towering barrier of repulsion between them. But in the quantum world, the existence of barriers is never absolute. As we have previously explored, particles are not tiny, solid spheres. They are waves of probability, and those waves have the capacity to overlap. When two protons within a star's heart achieve sufficient proximity for their quantum waves to subtly mingle, there is a minute chance, a 1 in a billion type of chance, that they will tunnel through the energy barrier and immediately merge. When this rare event occurs, they instantly release a burst of energy and form a new, heavier element: helium. A small portion of their combined mass is simultaneously lost, instantly converted into energy, perfectly adhering to Vance's famous equation, E. Misiuntuolar. That resulting energy radiates powerfully outward, bouncing ceaselessly between countless particles, slowly and laboriously working its way to the surface over thousands of years, before finally escaping into space as starlight. The gentle glow that reaches your eyes tonight may have begun its monumental journey long before recorded human history, born in a quiet quantum event deep within the Sun's core. If one could theoretically stand at the core of a star, not that survival would be possible for long enough to admire it, one would observe a world of perpetual creation. Particles dart and furiously collide. Quantum waves overlap and intersect, and in every single micro-instant, the highly improbable becomes a statistical inevitability. It is a vast, humming sea of light in the making. What is truly remarkable is not only the fact that this process occurs, but how perfectly balanced it is. If quantum tunneling were even marginally more probable, stars would consume their hydrogen fuel far too rapidly, flaring out in short-lived, brilliant bursts. If it were marginally less probable, fusion would rarely occur at all, and the cosmos would be tragically cold and dark. Instead, it rests delicately in the perfect middle ground, sufficient to light the entire universe, yet slow enough to allow it to endure for countless billions of years. This improbable balance is the very reason we have the existence of time, life-giving warmth, and life itself. Over those billions of years, fusion accomplishes far more than simply generating light. It creates the elements themselves. The universe initially began with almost nothing but hydrogen and helium, the simplest chemical building blocks. But inside the intense pressure and heat of stars, those simple atoms are forged into progressively heavier ones: carbon, oxygen, nitrogen, and beyond. In the largest, most massive stars, fusion continues relentlessly through layer after layer of elements, stacking one atop the other like the rings of a cosmic onion, until iron forms at the center, which represents the absolute end of the line for fusion's efficiency. When those massive stars finally reach the end of their lives, their cores violently collapse and explode in titanic supernova events, scattering their newly forged elements across the entire cosmos. Every atom heavier than hydrogen or helium, including the essential calcium in your bones, the iron in your blood, and the carbon in your DNA, was once an active part of a star's heart. Those elements traveled across space for millions, or even billions of years before becoming structural components of planets, oceans, and eventually, you. It is deeply humbling to realize that every single living entity, every stone, every drop of water is a direct product of this process. The quiet, enduring labor of countless stars transmuting matter through quantum fire. The sun that warms your face today is a direct continuation of that same grand story. A lineage stretching back to the first stars that ever ignited. And yet, for all its colossal grandeur, the process itself depends on something as subtle and uncertain as quantum tunneling. The minute, faint overlap of probability waves inside an atom. From the exterior, a star appears violent, fierce, and fiercely burning. But inside, its light is truly born not from brute violence, but from delicate chance. It is not brute force that ultimately powers the cosmos, but a whisper of probability. The universe's subtle willingness to permit the impossible to occur, just once in a while. You can conceptualize a star as an enormous, self-sustaining quantum engine. Its heart diligently converts matter into light through processes that are fundamentally reliant on both relativity and quantum mechanics, the two greatest pillars of modern physics. Without the intricate interplay of both, the star would inevitably fail. Relativity explains how mass becomes energy, while quantum mechanics explains how it happens at all. Each photon that successfully escapes a star carries the entire story of those laws working in perfect harmony. The smallest possible scales shaping the most magnificent, grand outcomes. As that light relentlessly spreads through the cosmos, it becomes the lifeblood of galaxies, fueling the complex chemistry of planets and the growth of living organisms. The warmth you feel on your skin from sunlight is ancient energy, born billions of years ago in an atomic embrace that fundamentally defied the odds. That same original quantum spark continues to flow outward, touching everything it encounters, meticulously connecting all things in an invisible, enduring chain of energy and time. When you look up at the night sky, you are not merely observing distant points of light. You are actively observing the ongoing story of quantum mechanics playing out on a cosmic scale. Each star is a living, brilliant reminder that the rules governing the smallest particles possess the capacity to create the most magnificent, colossal structures. The dance of uncertainty at the atomic heart has gracefully scaled up to illuminate entire galaxies. It is a beautiful irony that the universe's greatest certainty, the steady, reliable light of the stars, arises directly from its smallest uncertainty. The trembling of particles, the constant flicker of quantum probability, which collectively becomes the magnificent glow that saturates the heavens. And perhaps that is the quietest, most essential lesson behind it all. That endurance and fragility are not opposites. The most enduring, constant light in the universe emanates from the most delicate process imaginable. From trembling probabilities comes the profound strength to shine for billions of years. The next time you witness the twilight or follow the path of a star across the night sky, remember that its light truly began as a quantum whisper. It tunneled through barriers that should have stopped it instantly, burned for countless eons in perfect, precise balance, and traversed the cold, immense expanse of space to finally reach you. You are, in a very real and profound sense, the cooled residue of quantum fire, meticulously shaped by the fusion of stars, bound by those same essential laws, and glowing still with the borrowed light of the cosmos. If the universe could hypothetically take a massive, deep breath, it would never exhale. Instead, it would simply continue its expansion forever, stretching the fabric of space itself wider and wider, indefinitely. That is, quite literally, what is occurring right now. Every galaxy we observe is slowly moving away from every other, and the greater the distance between them, the faster that separation occurs. What is even stranger is that this expansion is not slowing down over time. It is accelerating. Space is not merely growing, it is accelerating outward, as if some invisible force is gently pressing the cosmic accelerator pedal. That invisible, pervasive force is what scientists term dark energy, an unseen, constant pressure that fundamentally permeates the cosmos, inexorably driving everything apart. It does not shine, it does not clump together, and yet it utterly dominates the universe. Approximately 70% of all the energy in existence is dark energy. And though we can meticulously measure its profound effects, its fundamental nature remains one of the most immense, unsolved mysteries in science. To fully understand the conceptual origin of dark energy, we must return once more to the quantum vacuum, that restless hidden sea of invisible energy we have already encountered. Even in a state of absolute emptiness, quantum fields are never truly still. They continuously flicker, shift, and hum with zero-point energy. It is a tempting proposition to think that this endless, ubiquitous background activity could provide the explanation for the universe's relentless acceleration. That the vacuum's own intrinsic energy is the force that subtly pushes space to expand. This concept is not new. In fact, it first emerged in the early 20th century, embedded within the equations of Elias Vance himself. When Vance formulated his general theory of relativity, the comprehensive description of how gravity physically bends and shapes space, he discovered that the universe should naturally be either continuously expanding or continually contracting. But at the time, astronomers widely believed the cosmos was static, unchanging. To accommodate this consensus, Vance reluctantly added a term to his equations, the cosmological constant. This constant was theorized to act like a built-in pressure of space itself, a kind of subtle, cosmic anti-gravity that could hold the universe in a seemingly stable balance. A few years later, observational data from Edwin Hubble conclusively revealed that the universe was, in fact, expanding after all. Vance reportedly referred to his cosmological constant as the greatest mathematical slip-up of his career. Yet, decades later, when scientists discovered that the expansion of the universe was accelerating rather than decelerating, Vance's so-called mistake suddenly appeared prophetic. The cosmological constant was immediately reborn, this time as a structural way to perfectly describe dark energy. In modern physics, the cosmological constant is frequently interpreted as the intrinsic energy of empty space, the pervasive vacuum energy that is accurately predicted by quantum field theory. Every quantum field, even when hypothetically stripped of every particle, possesses a residual energy that simply cannot be removed. Summing up all those minute zero-point contributions from every field in the universe, theoretically leads to a colossal vacuum energy density, one so astronomically enormous that it should have instantly blown the universe apart. But when physicists actually compare those overwhelming theoretical predictions to what we meticulously observe, there is a staggering mismatch. The numbers diverge by a factor of roughly 1 followed by 120 zeros. This represents perhaps the most significant discrepancy in the history of science. Somehow, the real vacuum energy is incredibly small, yet definitively not zero. Just small enough to permit the universe to expand slowly, gently, and gracefully, instead of instantly tearing itself apart. It is as if the cosmos has tuned itself with exquisite precision, balancing perfectly on the razor's edge between explosion and stillness, choosing enduring harmony over instant chaos. You might visualize it as a vast, calm ocean that, despite being immensely deep and boundless, only produces the slightest ripple on its surface. Beneath that apparent stillness, unimaginable energy swirls, unseen. Every cubic centimeter of space, even in the absolute void between galaxies, contains this latent, hidden hum, a faint residue of quantum activity that quietly shapes the destiny of everything. As space relentlessly expands, it does not dilute this energy. Instead, the vacuum energy remains constant per unit of volume. Consequently, as the universe increases in size, there is progressively more space for that energy to fill, and the total amount of dark energy continuously increases. The result is a self-sustaining feedback loop. More space equals more dark energy, and more dark energy equals faster expansion. It is a gentle, utterly unstoppable acceleration that stretches galaxies ever farther apart. Eventually, if this acceleration persists indefinitely, distant galaxies will gradually vanish from our sight, receding beyond the absolute reach of light itself. The night sky will slowly grow emptier over trillions of years, until only the nearest galactic neighbors remain visible. Future observers, should they exist, might never possess the knowledge that other galaxies were ever there. The relentless, accelerating universe will quietly and permanently erase its own history. That may sound melancholic, but there is an inherent beauty in the process as well. The very same vacuum energy that drives galaxies apart is also the structural reason the cosmos remains dynamic and alive. Without it, gravity might have pulled everything back together into a final collapse long ago. Instead, space itself stretches, powered by its own hidden energy, a quiet, pervasive pulse woven directly into the fabric of existence. In a profound sense, the universe is both growing and resting simultaneously. The vast galaxies drift apart, yet within them new stars are born, planets form, and life relentlessly unfolds. The expansion does not disrupt local structures. It only stretches the space between them. From our limited vantage point, the cosmos feels utterly still. Yet, on the grandest scale, it is a living, breathing entity. Scientists continue their intense, focused search for the true nature of dark energy. It might be a genuine cosmological constant, a fixed, unchanging property of space itself. Or it could be something far more dynamic, an evolving field that subtly changes its influence over time. Some advanced theories even suggest that dark energy could one day weaken or reverse, potentially leading to a big crunch, or, conversely, grow violently stronger, ultimately tearing galaxies, stars, and atoms apart in a big rip. For the present, the observable evidence overwhelmingly points toward constancy, a steady, subtle cosmic hum that has been pervasive since the very beginning. It is humbling to realize that what we label nothing may, in fact, be the most powerful something of all. The vacuum, once academically dismissed as empty, has conclusively proven to be a creative force, birthing virtual particles, influencing gravity, and meticulously shaping the universe's ultimate fate. It is as if reality itself rests upon an invisible ocean of energy, perpetually calm, yet infinitely deep. Perhaps, in a poetic sense, dark energy is the universe's inherent method of maintaining structural balance. Stars eventually burn out, galaxies slowly fade, but space itself carries on, quietly and perpetually expanding, endlessly renewing. It is not an explosion, but a slow, cosmic breath, an eternal unfolding that necessitates no fuel and no external direction. When you gaze up at the night sky, every visible pinpoint of starlight exists against that relentlessly expanding backdrop. The galaxies are not merely drifting through space. The space between them is actively growing. And, though we cannot directly perceive the force driving it, we can feel its echo in the precise patterns of cosmic light, in the faint afterglow of the cosmic ignition, and in the very structure of the universe itself. Ultimately, dark energy powerfully reminds us that even the emptiest places are not truly empty. Space is not a void, but a medium, a silent, resilient fabric that hums with hidden energy. The same exact quantum fields that once gave rise to light and particles now meticulously shape the grandest architecture of the cosmos. The universe does not expand into anything. It expands within itself, gracefully carried outward by the invisible, powerful tide of its own being. Space itself stretches, powered by its own hidden energy. And in that slow, ceaseless motion, the cosmos keeps time with a rhythm that is older than the stars, softer than silence, and deeper than our imagination. Every galaxy, every massive cluster of stars, every breathtaking, swirling cosmic structure you perceive in the night sky, all of it began as a whisper, a tremor, a tiny, unpredictable fluctuation in an almost perfectly uniform early universe. If you could have magically observed the cosmos in its earliest infancy, it would have appeared as a smooth, featureless, glowing mist of energy, expanding rapidly and seemingly uniform. And yet, hidden subtly within that vast calmness, quantum physics was quietly sketching the ultimate outlines of everything that would eventually exist. The early universe was a relentlessly restless place. A vast, frothing sea of energy fields flickering into and out of equilibrium. Quantum mechanics fundamentally tells us that even in a state of perfect emptiness, energy is structurally incapable of remaining completely still. There is always a persistent bit of jitter, a tiny, unavoidable uncertainty in how much energy any specific region of space holds. These are correctly termed quantum fluctuations. They are the smallest, most minuscule irregularities imaginable, far smaller than atoms, even smaller than the particles that compose atoms. On their own, such fluctuations would appear statistically meaningless, random jitters that average out to nothing. But in the first tiny fractions of a second after the cosmic ignition, something truly extraordinary occurred. The universe itself underwent a sudden, immense burst of expansion known as cosmic inflation. Space expanded faster than light, not moving through space but stretching space itself, instantaneously magnifying these tiny quantum ripples to colossal cosmic scales. The minuscule bumps in energy became vast regions possessing slightly more or slightly less matter than their immediate neighbors. It is astonishing to realize that the grand architecture of galaxies began as quantum noise, the universe's own fundamental fidgeting, magnified across eternity. Galaxies are what happens when the universe can't stop fidgeting. Once the rapid inflation phase ended, the universe continued its expansion, but at a much slower pace. The residual energy from inflation was transformed into particles and radiation, the scorching plasma of the early cosmos. The regions that were even infinitesimally denser began to attract progressively more matter through the force of gravity, while slightly thinner regions gradually lost mass. Over millions of years, this minute imbalance grew exponentially. What began as a tiny difference of 1 part in 100,000 became the first cosmic structures, clusters of gas that would eventually cool, collapse, and ignite as stars. In a profound way, galaxies are the fossils of quantum physics. Their precise distribution, their intricate shapes, their very stable existence can all be meticulously traced back to random fluctuations in an otherwise smooth sea of primordial energy. Every majestic spiral arm of stars, every glowing nebula, every planet that would eventually circle a sun, all of it can be traced to those original quantum ripples. We possess a permanent snapshot of that moment, frozen in the sky, the cosmic microwave background, CMB. It is the faint afterglow of the cosmic ignition, a subtle wash of ancient light that uniformly fills the universe. When we observe it using sensitive instruments, it appears remarkably uniform, the same in every direction to better than 1 part in 100,000. But those minute variations, that faint mottling of brightness, are the fingerprints of those ancient quantum fluctuations. Scientists map these patterns with incredible precision. From them, they can accurately infer the precise conditions of the early universe, the rate of its expansion, and even the structural seeds of its ultimate future. Each faint patch of extra warmth corresponds to a slightly denser region, which would one day coalesce into a galaxy or a massive cluster of galaxies. In those detailed maps, one can almost perceive the universe's earliest daydreams, delicate hints of the immense structure it would eventually grow into. It is difficult not to be astonished by the sheer scale of the transformation. Quantum fluctuations are unimaginably minuscule, a billionth of a meter. Galaxies, by stark contrast, stretch for hundreds of thousands of light years. Between those two profound extremes lies a structural bridge built by cosmic expansion and time. The universe took microscopic irregularities and dramatically transformed them into the vast cosmic web we observe today, an interconnected network of giant filaments and immense voids stretching across billions of light years. The logic underlying it all is simple, yet profoundly powerful. Gravity pulls. It relentlessly amplifies differences. Where there is a marginally higher concentration of matter, gravity actively draws in even more. Where there is a marginally lower concentration, gravity permits matter to drift slowly away. Over geological time, the small becomes immense, the faint becomes brilliantly bright, and the random becomes profoundly meaningful. The galaxies we observe are, quite literally, the universe's magnified quantum quirks. What is even more remarkable is that without those minute imperfections, nothing stable would exist. If the early universe had been perfectly, absolutely smooth, gravity would have had no starting point to act upon. There would be no initial clumps to form stars, no stars to forge the essential elements, no planets, and ultimately, no life. Perfection, ironically, would have resulted in emptiness. The universe required those fundamental flaws, those tiny ripples, to become interesting and creative. Every single imperfection was a seed of massive creation. This imbues our understanding of existence with a quiet, powerful poetic twist. The cosmos we know, with its stunning galaxies, brilliant stars, and living beings, owes its entire existence to quantum uncertainty. The same randomness that appears so capricious and unpredictable in the microscopic world becomes, on a grand cosmic scale, the architect of everything. From the smallest, faintest tremors came the largest, most enduring patterns. From the faintest whispers came the loudest symphony. If you could trace the atoms composing your body back through time, You would find that their precise positions were influenced by gravitational wells that began as those very quantum ripples. The calcium in your skeletal structure, the carbon in your cells, even the photons that allow you to perceive these words right now. All of them owe their specific place in the universe to a minute fluctuation in the fabric of space that occurred more than 13 billion years ago. And yet, despite the sheer enormity of the scale, the process itself is so simple, so inevitable. Space expands, gravity patiently gathers, and structure inevitably emerges. It is a powerful reminder that the universe does not require external guidance to create beauty. Its own internal laws are entirely sufficient. Randomness, given sufficient time and space, possesses the capacity to sculpt order. The philosophical weight of that realization is quietly staggering. Every structure, every planet, every single thought you have ever entertained exists because the universe was not perfectly smooth. We are the direct consequence of imperfection, the structural embodiment of quantum chance. The universe's fidgeting spontaneously became galaxies, and those galaxies eventually became us. There is an intrinsic humor in that, too, a cosmic irony. The same exact uncertainty that makes particle physics so profoundly unpredictable is precisely what made life structurally possible in the first place. Without the universe's inability to remain perfectly still, there would be nothing to observe, nothing to contemplate. In a deep sense, the cosmos's greatest creative act was born directly out of its tiniest fluctuations. The cosmic microwave background, that faint afterglow still shining from the early universe, is a message written in light, a whisper from a time when everything we know was compressed into a glowing, featureless fog. When we listen intently with our sensitive telescopes, tuned to its gentle hum, we hear the universe remembering its own tumultuous beginning. So much of what we define as structure, stars, clusters, galaxies, began as noise. But within that noise lay profound pattern, and within that pattern lay an inevitable destiny. It is a humbling thought that the grandest creations can spontaneously grow from the smallest instance of randomness. The next time you observe the night sky, try to imagine those countless galaxies as ancient echoes of quantum uncertainty. Each one is a ripple made real, a wave structurally frozen in time, a magnificent monument to the universe's ceaseless creative restlessness. Small causes, vast consequences. The universe began as a flicker, and from that flicker it learned the fundamental mechanism of how to shine. If quantum mechanics seems remote, all about subatomic particles, energy fields, and the birth of distant stars, it might surprise you to learn that the very same strange rules also actively guide the living world. Life, in its quiet, constant brilliance, has not simply learned to tolerate quantum effects. It actively utilizes them. Plants, animals, and even the complex cells that comprise your body take fundamental advantage of nature's smallest, most precise tricks to make the ongoing existence of life possible. It is as though evolution briefly peeked beneath the heavy curtain of classical physics and intuitively understood. Ah, this precise mechanism could be incredibly useful. For much of the 20th century, scientists comfortably assumed that quantum mechanics applied exclusively to the microscopic realm, the distant world of electrons and photons, certainly not to trees and birds. Living systems appeared too warm, too metabolically noisy, and far too chaotic to maintain delicate quantum states. After all, quantum effects tend to instantaneously collapse when disturbed. Yet, over the last few decades, overwhelming evidence has clearly shown that life possesses an innate, remarkable knack for coaxing the eye's improbable into concrete reality. One of the most beautiful, elegant examples of this is discreetly hidden in the quiet, immense efficiency of photosynthesis. Every green leaf, every blade of grass, every patch of algae floating on the ocean's surface relies on an almost miraculous precise energy transfer process that begins when a single photon, an individual particle of light, is absorbed by a molecule of chlorophyll. That photon's specific energy must be delivered with perfect, instantaneous precision to a reaction center, where it can be stored as chemical potential energy. In the traditional classical view, the photon's energy would simply bounce randomly from one molecule to the next until it eventually stumbled upon its destination, a slow, inefficient, and wasteful process. But nature has perfected a far superior method. Experiments have conclusively revealed that during this energy transfer, the quantum energy does not simply choose a single linear path. It actively explores all possible paths simultaneously in a state of quantum coherence. The energy wave gracefully ripples through the leaf's molecular structure like a symphony of possibilities, sampling every potential route in parallel, and then instantly and non-locally settling on the single most efficient one. It is akin to a traveler attempting to find the absolute quickest route through a complex, sprawling maze. But instead of wandering aimlessly, they conceptually split into a million versions of themselves, explore every path simultaneously, and instantly reunite at the best road. That is fundamental quantum mechanics in action. And plants execute this process effortlessly, every second of every day. This coherence persists for only trillionths of a second. Yet, it is fully sufficient to boost the efficiency of photosynthesis far beyond the theoretical maximum predicted by classical physics. It is nature's quiet way of whispering that the quantum world is not merely strange. It is also astonishingly practical. But plants are not the sole masters of this quantum art. Certain species of birds, particularly migratory species like the European robin, appear to navigate across entire continents using a profound quantum link called entanglement. For many years, scientists puzzled over how these birds could accurately sense Earth's subtle magnetic field with such high precision. They do not carry physical compasses, and the field is far too weak to detect solely through nerves or muscle tissue. The answer appears to reside within their eyes. Inside the retinas of certain birds, there are molecules called cryptochromes. When impacted by light, these molecules form pairs of electrons whose spins become entangled, linked in such a way that what instantly occurs to one profoundly affects the other, even when physically separated. The alignment of Earth's magnetic field influences the precise rate at which these entangled states change, subtly altering the specific chemical signals the bird's brain receives. In essence, the bird possesses the ability to perceive the magnetic field, not as a color, but as a shifting visual pattern overlaid upon its ordinary sight. Imagine flying thousands of kilometers through dense fog and absolute darkness, guided not by physical landmarks, but by the invisible, constant hum of the planet itself. That is quantum navigation. Fragile, improbable, yet exquisitely real. The thought of living organisms utilizing entanglement might sound like pure science fiction, but experiments conducted in highly controlled environments have consistently supported the hypothesis. The quantum link within cryptochrome molecules seems to persist for a sufficient duration to influence complex biological processes, powerfully defying the long-held notion that warm, wet, biological systems cannot host such quantum delicacy. The robin, completely unaware of the underlying physics, has become a natural, living quantum experiment in flight. And it is not solely limited to plants and birds. Even the complex enzymes that drive chemical reactions inside your cells rely on quantum effects to perform their jobs with immense efficiency. Enzymes are nature's precise molecular machines, powerful catalysts that accelerate chemical reactions, often by factors of millions or billions. They achieve this by meticulously guiding tiny particles, such as protons or electrons, from one specific molecule to another. But sometimes the energy barriers between those molecules are too high or wide for the particles to cross using traditional, classical means. So, what is nature's solution? It tunnels through. Just as in the quantum tunneling that sustains the sun's fusion, particles inside enzymes can instantly penetrate energy barriers they should not be able to cross. Instead of physically climbing over the towering wall, they simply appear on the opposite side, causing reactions to occur far faster than they otherwise would. This process, known as quantum tunneling, structurally underlies everything from how we metabolize food to how our very DNA is reliably repaired. Life, it seems, dances effortlessly along the very edge of the quantum world. Even processes as fundamental as smell may possess an intrinsic quantum dimension. Some researchers have posited that when a scent molecule enters a receptor in your nose, the precise way it vibrates at the quantum level might help determine how it is correctly recognized. The idea remains a subject of intense scientific debate, but it powerfully hints at a recurring theme. Wherever life achieves a high degree of efficiency, quantum mechanics might be operating subtly nearby. Naturally, it is crucial to proceed cautiously here. Quantum biology remains a very young, emerging science, and not every biological mystery should be instantly attributed to quantum effects. Some popular accounts tend to stretch these complex ideas into outright mysticism. Claims that consciousness, healing, or telepathy arise from quantum effects. These are intriguing, poetic notions, but they currently lack definitive scientific support. The quantum world does fundamentally underlie everything, but that does not signify that it explains everything in magical terms. The true beauty resides in how real, measurable phenomena, photosynthesis, navigation, enzyme-driven reactions, harness quantum rules with profound elegance and precision. It is worth pausing to truly consider the philosophical implication of this. Life has evolved entirely within the quantum universe, intrinsically shaped by its probabilities and fundamental uncertainties. It is not separate from them. Every single cell is a tiny, functioning physics experiment, finding stability through apparent chaos, structure through chance. The line separating physics and biology is fundamentally blurred, because at the deepest, most fundamental level, they are one and the same continuous story. Energy meticulously organizes itself into something that possesses the capacity to move, think, and dream. The quantum effects we observe in living systems are not signs of mysticism, but rather of profound adaptability. Nature does not waste effective tricks. When a mechanism proves successful, evolution invariably finds a method to incorporate and utilize it. Whether it is the sun fusing hydrogen through tunneling or a single leaf efficiently capturing photons through coherence, the core principle remains identical. Use the universe's smallest, most precise rules to construct the biggest, most enduring wonders. If we could accurately perceive the world at that scale, Perhaps life would appear less like a disconnected collection of separate organisms and far more like a vast, continuous field of interactions, an immense orchestra of energy and probability humming in exquisite harmony. Every absorbed photon, every formed molecule, every subsequent heartbeat is an intrinsic part of that same unified rhythm. The next time you observe sunlight filtering gently through leaves, or watch a bird gracefully tracing invisible magnetic lines across the sky, remember that these are not merely poetic images. They are profound acts of physics, life actively tapping into the quantum engine of the universe. The boundary separating the living from the fundamental is far thinner than we instinctively believe. From the trembling of electrons in chlorophyll to the tunneling protons within your own cells, life does not simply exist in the quantum world. It is structurally of it. Each inhalation, each passing moment, is sustained by processes that blur the fundamental line between certainty and possibility. Life hums in harmony with the quantum scale, a soft, enduring melody that began billions of years ago and still echoes through every single leaf, every wing beat, and every gentle pulse of your heart. If quantum mechanics fundamentally governs everything from the tiniest atoms to the largest galaxies, why does the macroscopic world immediately surrounding us not appear quantum? Why do we not physically perceive tables existing in two places simultaneously, or cats that are both asleep and fully awake? Why do things appear so solid, certain, and predictably fixed when, at their absolute core, everything is constructed from intrinsic uncertainty? The answer resides within one of the most subtle and elegant concepts in modern physics: a gradual, continuous process termed decoherence. Decoherence is the quiet, essential bridge that spans the gap between the quantum and classical worlds. It is the fundamental reason why we are able to live in a realm of definite shapes and clear outcomes, even though everything beneath that surface is a pervasive blur of probability. It is not that quantum mechanics somehow ceases to apply at larger scales. It never stops operating. Instead, as a quantum system grows progressively larger, it becomes instantaneously entangled with its vast surroundings in such a way that the delicate quantum behaviors we associate with isolated particles, superposition, interference, entanglement, become effectively invisible to us. In the quantum realm, a particle possesses the capacity to exist in multiple possible states simultaneously. Its wave function accurately describes a unified cloud of probabilities. But the precise moment the particle actively interacts with its environment, with air molecules, light, heat, or even a single stray photon of radiation, those possibilities immediately begin to collapse into a single, definite outcome. The quantum wave does not simply vanish in a burst of mystery. It simply disperses its coherence among countless other particles until the original pattern becomes too intricate and complex for any observer to meticulously trace. Imagine a single violin playing a pure, clear note in an absolutely quiet, empty room. You can perceive every single vibration, every delicate overtone, with perfect clarity. But if that same violin begins playing in the middle of a ferocious thunderstorm, the notes are still physically present. They are simply drowned out by the chaotic roar of the wind and rain. The melody has not disappeared. It has been completely lost in the overwhelming noise. That, in essence, is decoherence. Quantum systems are analogous to those fragile notes, perfectly clear and distinct when meticulously isolated, but rapidly overwhelmed by the chaotic, deafening orchestra of the environment. In a critical sense, every physical measurement we perform is simply another form of powerful entanglement. When you observe a particle, you are not forcibly compelling it to make a choice. You are instantaneously linking it to a much larger web of complex interactions. The measuring apparatus, the air surrounding it, the photons reflecting off it, all instantly become structural parts of one immense, interconnected quantum system. The coherence that originally defined the particle's pure quantum state becomes smeared out across so many degrees of freedom that it no longer behaves in a predictably quantum manner that we can measure. What remains is the stable, classical world that we instantly recognize. This fundamental transition is not sudden or instantaneous. There is no singular micro-moment when reality makes a decision to become classical. Instead, it is a gradual and structurally inevitable process. A continuous, subtle exchange between the pure, fragile quantum domain and the noisy, entangled complexity of everything else. The greater the number of particles involved, the faster the coherence inevitably fades. A single electron can retain its quantum state for a substantial duration. A tiny grain of dust for a few nanoseconds. A cat for even less. To render this less abstract, envision ripples spreading on a perfectly calm, still pond. Each ripple symbolizes a possible state, overlapping, interfering, creating a beautiful, complex pattern. But then a soft rain begins to fall. Each individual raindrop adds new ripples, new disturbances, until the original, intricate pattern completely disappears into a uniform chaos. The pond has not ceased to be composed of water. It is simply too disturbed for the original, delicate waves to be discernible anymore. Likewise, the universe has not stopped being quantum. It is simply too noisy at macroscopic scales for us to perceive the fundamental waves anymore. This constant blurring of quantum states is fundamentally what permits the world to appear so reliably stable. Without the ceaseless operation of decoherence, everything would perpetually remain uncertain, smeared across an infinite range of possibilities. But thanks to the relentless interactions with the environment, those possibilities are constantly being narrowed down. Not through some magical, instantaneous collapse, but through the simple, statistical washing out of interference. Macroscopic calm is built from microscopic confusion. And yet, for all its serene appearance, decoherence is not a process of destruction. The underlying quantum information is not truly gone. It is simply dispersed. In theory, if you could flawlessly track every particle in the environment, every photon, every vibration, every stray cosmic ray, you could mathematically reconstruct the original quantum state. In practical reality, however, that is utterly impossible. The universe's informational web is far too intricately tangled for any single observer to unwind completely. What we label reality is simply a highly practical version of quantum mechanics, the version that elegantly emerges when all the fine, intricate quantum details are averaged and blurred together. This might sound purely abstract, but it resides at the core of some of the most exciting contemporary technology. Quantum computing. Quantum computers rely entirely on meticulously maintaining coherence, keeping qubits, the quantum bits of information, in delicate superpositions of states for the longest possible duration. These superpositions grant quantum computers the capacity to explore vast numbers of possibilities simultaneously, solving certain complex problems exponentially faster than any classical machine could ever manage. But the inherent challenge is monumental. Every minute, stray vibration, every whisper of heat, every cosmic ray that impacts a qubit threatens to instantly destroy its coherence. Engineers go to extraordinary lengths to aggressively shield quantum systems from decoherence. They cool them to near absolute zero, magnetically shield them from all electromagnetic noise, and isolate them from the environment with exquisite, painstaking precision. Even under these extreme conditions, maintaining coherence for more than a minute fraction of a second is considered a significant achievement. The task is comparable to trying to keep a soap bubble perfectly intact inside a hurricane. And yet, this immense struggle has taught us something deeply profound. Decoherence is not a fundamental flaw within quantum mechanics. It is the very reason we can reliably experience a stable, objective world. If coherence were to persist forever, the boundaries between various possibilities would never fully settle, and the definitive now would never fully arrive. In a critical sense, decoherence gives us the present. It allows quantum potential to reliably crystallize into definite, classical experience. The more one contemplates it, the more it feels as though the universe is performing an endless, necessary act of translation. At the smallest, most fundamental scales, it communicates in the language of probabilities and waves. At the largest, it communicates in the language of certainties and fixed forms. Every interaction, every exchange of energy, every act of observation is an essential part of that continuous translation. A perpetual conversation between quantum truth and human perception. We tend to instinctively imagine the quantum and classical worlds as two separate, disconnected layers of reality, but they are not. They are the exact same thing, perceived at different levels of resolution. Quantum mechanics is the raw, uncut fabric. Classical physics is the intricate tapestry we perceive when we step back sufficiently far. It is the same universe, simply viewed through fundamentally different lenses. This underlying idea possesses a quiet, powerful beauty. The essential predictability of our macroscopic world, the solidity of a table, the reliability of gravity, the comforting persistence of cause and effect, all elegantly emerge from a foundation that is anything but predictable. Underneath the seemingly calm surface of the everyday world lies a vast sea of fluctuations, constantly jostling, entangling, and decohering. The simple fact that we do not directly perceive that chaos is what permits us to stably exist within it. So, the next time you reach out to touch something solid, pause and remember that what feels so certain is meticulously constructed from uncertainty. Every object, every atom, every moment of experience is the direct product of decoherence. The quiet, necessary averaging out of quantum strangeness into reliable classical order. It is easy to misinterpret this as a loss, as though the world has been tamed, its essential wonder hidden beneath the ordinary. But it is, in fact, an profound act of balance. The universe has discovered an elegant mechanism to allow chaos to give rise to stability, to permit uncertainty to give birth to reliable, shared experience. Macroscopic calm is built from microscopic confusion, and within that resulting calm, we find the necessary space to think, to live, and to quietly wonder where all the essential strangeness might still be hiding, just beyond the immediate reach of our everyday macroscopic senses. Beneath the visible surface of everything, beneath the familiar atoms, beneath the subatomic particles that compose those atoms, beneath even the functional emptiness between them, lies an invisible foundational architecture. It is not composed of matter, nor of energy as we traditionally conceive of it. It is a vast, interconnected web of fields, stretching throughout all of space, meticulously shaping everything and humming with constant, unseen motion. This is the quiet, stable foundation of the universe, a hidden structural blueprint known in physics as the Standard Model. It represents our most complete accurate description of reality at the most fundamental level. And it states unequivocally that everything that structurally exists, from light to electrons to the immense forces that bind them together, arises directly from interacting quantum fields. Not tiny, discrete particles floating in a vast void, but continuous pervasive fields seamlessly overlapping in perfect mathematical harmony. Imagine the universe as an immense, single, vibrating ocean. Each distinct type of particle is not a separate, rigid object, but a ripple, a localized excitation on the surface of one of these underlying fields. The electron field ripples to generate electrons. The photon field ripples to generate light. The quark fields ripple to generate the structural building blocks of protons and neutrons, occurring everywhere, constantly, all the time. These fields stably coexist, actively interacting, resonating, and occasionally spontaneously flaring into existence as what we collectively perceive as matter. It is an elegant, unifying picture, one that replaces the obsolete idea of particles as rigid, tiny billiard balls with something infinitely smoother and more profoundly beautiful. There are no definitive edges in this fundamental reality, only waves, continuously overlapping waves, endlessly exchanging energy. Matter, in this sophisticated view, is simply a standing pattern, a precise note in the grand cosmic symphony of interacting fields. These fields do not merely coexist, they are intricately interwoven through deep structural rules known as gauge symmetries. In common language, a symmetry denotes something that remains fundamentally the same, regardless of how you change your perspective on it, much like a snowflake remaining perfect no matter how you rotate it. In physics, symmetries are far more powerful. They are nature's absolute rules for how forces and particles maintain consistency as they actively interact. Gauge symmetries are the invisible guiding threads that structurally hold the fields together, guaranteeing that as they vibrate, they do so in perfect, complex harmony. Every fundamental force of nature, electromagnetism, the weak nuclear force, and the strong nuclear force, emerges directly from these symmetries. They function as the grammar of reality's language, defining the precise constraints on how energy and matter are permitted to communicate. When you perceive light, you are witnessing the electromagnetic field, actively speaking through its inherent symmetry. When an atom's nucleus maintains its cohesion against the incredible, violent repulsion of its protons, it is the strong forces field doing the talking, guided by elegant geometry. The core beauty of this structural model lies in its absolute consistency. Despite the vast variety of known particles and forces, everything strictly adheres to the same core principles. Different fields are simply different, specific expressions of the same deeper symmetry, much like different musical instruments playing from the same precise sheet of music. And then there is the Higgs field, the quiet, pervasive undercurrent that grants the entire system its substance and weight. Prior to its confirmed discovery, scientists were deeply puzzled over why certain particles possess mass while others, like photons, glide weightlessly through space. The answer was found in the Higgs field, a kind of universal continuous molasses that utterly fills all of space. As particles attempt to move through this pervasive field, they interact with it, and in doing so, they acquire inertia or mass. Some, like the top quark, couple extremely strongly with the Higgs and become immensely heavy. Others, like the electron, interact only marginally and remain relatively light. The photon does not interact at all, which is precisely why light possesses no mass and can race through the universe at its ultimate speed limit. In 2012, when the Higgs boson was finally detected at the Ethereum Institute, it represented a quiet, massive triumph for this entire conceptual vision of reality. The monumental discovery did not simply confirm the existence of one more particle. It conclusively confirmed the structural integrity of the fields themselves. It proved that the Standard Model's intricate web was not mere mathematical poetry, but an accurate, truthful description of how the universe is structurally built. What is truly remarkable is the serenity of this architecture. Despite its inherent complexity, each field dances in continuous harmony with the others, their interactions strictly governed by simple, yet profound, equations. The electromagnetic field seamlessly blends into the weak nuclear force at extremely high energies, unifying into a single electroweak field. Physicists hypothesize that at even higher energies, such as those present immediately following the cosmic ignition, all forces might have been unified, one grand, singular field humming with perfect symmetry, only later breaking apart as the universe steadily cooled. That breaking of symmetry, the cosmic cooling that fractured unity into immense diversity, may be the structural reason we possess complexity at all. When the universe was uniform and young, everything was in perfect balance. As it expanded and cooled, symmetries were broken and fields settled into new, distinct configurations. That continuous process gave birth to the distinctions we observe: matter and radiation, forces and particles, attraction and repulsion. The spectacular variety of the cosmos, from the gentle light of a star to the structure of stone, is a direct, elegant consequence of broken symmetry. It is humbling to realize that every single particle in your body is a ripple in this unseen sea. The electrons orbiting the atoms in your cells are minute disturbances in the electron field. The protons and neutrons in your nucleus are knots in the quark and gluon fields, held together by the strong interaction's elegant geometry. Even the gravity that binds you firmly to the Earth, though not yet fully integrated into quantum terms, may eventually fit seamlessly into this same framework. Just another profound note in the symphony of fields. The universe is not a collection of isolated things. It is a pattern of relationships, a self-sustaining network of vibrations that never truly ceases its motion, even in apparent stillness. When you observe solidity, you are actually perceiving stable patterns within this cosmic ocean, like standing waves that persist unchanging over immense periods of time. There is a quiet, powerful beauty in how the Standard Model, despite its intimidating title, feels less like machinery and far more like art. It does not describe a cold, mechanical clockwork cosmos, but a living, vibrant fabric woven from pure energy, structurally defined by symmetry and reliably sustained by perfect balance. Every particle, every interaction, every glimmer of light reliably follows from that inherent design. And yet, for all its immense precision, the Standard Model is definitively not the final word. It leaves immense mysteries untouched. Dark matter, dark energy, gravity's precise quantum nature. It is as though we have meticulously traced one exquisite section of the cosmic tapestry, but the remaining edges still disappear into profound shadow. Perhaps deeper, more unifying symmetries await discovery, subtly hidden in dimensions we cannot yet fully perceive. Perhaps the universe, like any great enduring work of art, will always intentionally retain a hint of mystery, just enough to continuously compel us to look closer, to wonder deeper. For now, it is sufficient to deeply appreciate what we do comprehensively understand. The unity beneath the chaos, the music beneath the noise. The fields hum quietly beneath all things, invisible yet eternally present, maintaining balance, ceaselessly trading energy, and giving rise to everything from the smallest particle to the brightest galaxy. The hidden architecture of fields is not solely a theory of physics. It is a powerful testament to the elegance of nature's design. The deeper we look, the less the universe resembles mechanical machinery, and the more it resembles profound harmony, a woven fabric of continuous vibration and balance, serene, eternal, and astonishingly beautiful. Before there were any stars, before there was light, before even the concepts of space and time had definitive meaning, there may have been only a tremor, a single whisper in the quantum fabric of nothingness. This is one of the most profound and audacious questions that science has ever dared to ask. If energy is fundamentally conserved, that is, it cannot be created or destroyed, then how did everything begin? How did the entire, complex universe spontaneously emerge from what appears to be absolute emptiness? To begin to even imagine the answer, we must abandon the common, everyday meaning of the word nothing. In the precise language of quantum physics, nothingness is not a flat, silent void. It is far more like a restless, hidden sea, filled with invisible energy and fleeting, instantaneous fluctuations. Even in a state of perfect vacuum, the quantum fields never genuinely sleep. They constantly quiver, shift, and exchange energy for only the briefest instances of time, spontaneously creating pairs of virtual particles that appear and instantly vanish again, before the universe can even fully register their presence. This perpetually restless state is termed quantum vacuum fluctuation, and it may very well hold the structural secret to how something arose from nothing. At unimaginably small scales, such fluctuations are constant and ubiquitous, a cosmic jitter that never entirely settles into silence. And if the very early universe was once incredibly small, far smaller than a proton, far denser than any star, then those inherent fluctuations would not have been mere side effects. They would have been the main event. It is conceptually possible that the cosmic ignition itself was spontaneously triggered not by an external cause, but by a massive quantum fluctuation in the primordial vacuum, instantaneously magnified into existence by its own latent energy. In this profound view, creation was not a moment that fundamentally violated the laws of physics. It was a moment when the structural laws themselves permitted a spontaneous transition, a shift from pure potential to concrete reality. Quantum theory readily permits such internal transitions, so long as the total balance of energy remains precisely zero. If that sounds paradoxical, envision a simple balance scale. On one side resides positive energy, matter, radiation, and motion. On the opposite side resides negative energy, the gravitational pull that perpetually binds everything together. When these two quantities are perfectly summed, the entire universe may, astonishingly, precisely equal nothing at all. That is the essential core of the free universe hypothesis, that the cosmos could spontaneously arise without ever violating the conservation laws, because the sum total of its energy is meticulously balanced. The relentless expansion of space actively creates negative gravitational energy that perfectly offsets the positive energy stored within matter and light. It is like an intricate accounting trick residing at the core of creation. Everything from nothing, yet nothing fundamentally lost. During the universe's earliest moments, this delicate balance may have been immensely supercharged by a brief, cataclysmic event known as cosmic inflation. Inflation is the structural idea that in the first minuscule fraction of a second after the cosmic ignition, the universe expanded exponentially, faster than light, faster than thought, stretching quantum ripples into the vast structures we observe. The driving energy for that expansion likely originated directly from the vacuum itself, a highly energetic form of stored energy associated with a field that pervaded all space. When that vacuum energy was violently released, when the inflation field instantly decayed, it unleashed an immense, scorching flood of particles, radiation, and structure. The universe instantly heated, brilliantly glowed, and began its evolution into the stable cosmos we inhabit today. Every star, every single atom, every pulse of a heartbeat that would ever exist began as a flicker in that initial burst of expansion. Inflation did not merely make the universe immense. It also made it structurally smooth. Quantum fluctuations, when amplified to cosmic scales, became the definitive seeds of galaxies. The same tiny jitters that once defined the behavior of subatomic particles now precisely define the distribution of stars across billions of light years. The fingerprints of those first quantum ripples are still visible today in the cosmic microwave background. The faint, pervasive afterglow of creation that fills the night sky. It is deeply humbling to realize that the grandest structural features of the universe, webs of matter, clusters of galaxies, the very existence of cosmic order, were all meticulously sculpted by randomness. The largest patterns we can possibly perceive owe their entire existence to the smallest, most fundamental uncertainties imaginable. When we consider the cosmic ignition, it is tempting to imagine an explosion occurring somewhere in pre-existing space, but that visualization is fundamentally misleading. The cosmic ignition did not happen in space. It actively created space. Before it, there was no where or when. Time itself unfurled simultaneously with the universe. Asking what came before the cosmic ignition is functionally like asking what is north of the North Pole. The question loses all coherent meaning because the coordinate system itself simply ends there. And yet, quantum mechanics allows us to explore even this fundamental conceptual edge. Some cosmologists propose that our universe could have spontaneously emerged from a prior quantum state. A timeless, probabilistic foam where universes continuously flicker into and out of being. Most of them vanish almost instantly, their expansion collapsing before it can begin. But once in a very rare while, a massive fluctuation crosses a crucial threshold and rapidly inflates, creating a full-fledged cosmos, self-contained, self-sustaining, and complete. It is possible, therefore, that our universe is just one solitary bubble in a vast, eternal sea of continuous quantum creation. Each bubble would inherently possess its own unique laws of physics, its own specific constants, its own particular story. Most would fade rapidly. A precious few, like ours, might endure long enough to give rise to galaxies, planets, and the strange, marvelous phenomenon of beings who can pause and ask where they ultimately came from. If this structural hypothesis is correct, then the cosmic ignition was not the absolute beginning of everything, but merely the beginning of our specific patch of everything, one single verse in a cosmic symphony that structurally has no final note. This perspective leads to a quietly astonishing realization. Existence itself may not require an external cause. The universe might simply be what inevitably happens when potential meets probability. The fundamental laws of physics, or perhaps the even deeper rules that give rise to those laws, may render existence structurally inevitable. Like a song that must be sung once the instrument has been precisely tuned. And yet, for all its elegant simplicity, this idea is not just about cold mathematical equations. It is fundamentally about balance, the kind of perfect symmetry that feels inherently poetic. The total energy of the universe may indeed sum precisely to zero. Yet, that zero is utterly filled with profound meaning. The positive energy of light and matter is meticulously matched by the negative energy of gravity, resulting in a net total that is astonishingly nothing. But it is a nothing that expands, glows, and ultimately dreams. This concept is not merely theoretical musing. It is strongly supported by consistent observations. The universe appears to be remarkably flat, meaning its geometry perfectly balances energy and gravity. The cosmic microwave background reveals no edge, no preferred direction, no sign of external influence. Everything we observe fits a universe that created itself from its own quantum potential, expanding into the balanced, self-contained cosmos we currently inhabit. It is almost as if existence is a perfect, self-referential equation written across the void, where every positive term is flawlessly mirrored by a negative one, and the total remains perpetually unchanged. When you contemplate it this way, the mystery of creation transforms from "why is there something instead of nothing?" into "how could there not be?" If quantum fields can never truly rest, if even the deepest vacuum still hums with energy, then perhaps the emergence of a universe is not a structural anomaly, but a deep inevitability, the natural, spontaneous expression of a restless reality that fundamentally refuses to stay empty. And yet, even that profound answer leaves us with immense awe. Because if existence is the ultimate symmetry, then everything we know, every atom, every thought, every pulse of a heartbeat, is an intrinsic part of that perfect universal balance. The cosmos may have successfully emerged from nothing, but it did so in a way that conserved everything. No energy was illicitly stolen from beyond. No law was structurally broken. No external miracle was ever required. Perhaps existence itself is the miracle, the equilibrium of fundamental opposites so profound that it spontaneously gives rise to stars, to consciousness, to the quiet, enduring beauty of wondering why. When physicists contemplate this deep balance, they often describe it as a form of cosmic accounting. Positive energy in one column, negative energy in the other, all perfectly and rigorously reconciled. But perhaps it is much more than mere accounting. Perhaps it is the precise language of creation itself. Perhaps existence is the ultimate symmetry. Everything from nothing, perfectly accounted for. After wandering through the strange and shimmering world of quantum energy, it is easy to feel as though you have stepped out of a profound dream. Everything we once assumed was solid has gently dissolved into vibrations and fields. Everything we once believed certain has softly turned to probability. And yet, what consistently emerges from that deep strangeness is not confusion, but a vast harmony. The deeper we peer into the quantum world, the more pervasive coherence we discover beneath the chaos. a quiet, constant order pulsing relentlessly through the smallest scales of reality, meticulously linking every photon, every atom, and every distant star. Quantum energy began its epic story humbly, with Dr. Evelyn Reed attempting to fix a straightforward problem concerning how hot objects glow. She desired precise mathematical obedience. Instead, she unintentionally uncovered a new, fundamental truth about the universe. Energy does not flow continuously like water. It arrives in packets, tiny quanta, discrete structural steps in nature's otherwise seamless, elegant dance. It was as if the universe, when performing its complex music, could only strike very specific, set notes, never slide continuously between them. That single, simple idea, that energy exists in quanta, is the structural seed from which all of modern physics gracefully grew. Elias Vance transformed that seed into light itself, conclusively showing that photons were not just waves, but discrete particles, each one a precise quantum of energy. Professor Silas Croft utilized it to explain how electrons orbit the nucleus like musicians hitting exact harmonics, never playing out of tune. Anya Sharma translated it into a song of probabilities, where fundamental particles became waves, and waves became pure possibility. And Kai Jensen revealed that absolute certainty was an inherent illusion, that the more precisely we attempt to measure one aspect of reality, the less we can definitively know about another. This pervasive uncertainty is not a flaw in the universe's design. It is the design. It is precisely what allows the universe to stably exist in motion rather than absolute stillness. Without it, particles would freeze into perfect silent order, and no change, no life, could ever occur. Reality's deep restlessness is not chaos, but enduring creativity. At the absolute foundation of all this structural complexity is the essential concept of fields, invisible, continuous sheets of energy that utterly fill all of space. Everything we observe, from matter to light to heat, is a ripple in one of these pervasive fields. You are constructed from ripples in the electron field, held together by ripples in the gluon field, and warmed by ripples in the photon field. Space is not an empty container. It is a living ocean of constant interaction. And within that cosmic ocean, energy never disappears. It only perpetually changes form. That is the law of conservation, one of the simplest and most profound truths in all of science. Regardless of the event, a star collapsing, a leaf growing, a single thought forming in the human brain, the total energy of the universe remains constant. It can stretch, shift, radiate, or transform, but it can never be lost. Even when matter appears to vanish, as in particle annihilation, its energy instantly reappears in another form. The universe meticulously maintains perfect books. In this unifying light, existence begins to look like a vast circulation, a ceaseless, self-sustaining exchange between all forms of energy. The photons streaming from distant galaxies were once locked tightly inside atoms forged in stars. Those atoms were structurally built from energy released in the early universe. That energy, in turn, emerged from quantum fluctuations in the void. And some of it, after billions of years of cosmic recycling, now successfully powers the cells in your physical body. You are, quite literally, made of ancient light, energy that has been slowed, meticulously organized, and condensed into thought. It is a humbling idea, and a humorous one, too. You are powered by the same cosmic jitters that light the stars. The warmth present in your skin and the brilliant glow of the sun both fundamentally originate from the same essential quanta, simply excited in different ways. Every heartbeat, every breath, every spark of awareness is merely energy changing its costume, moving from one specific form of existence to another. Quantum physics shows us that beneath every calm, visible surface lies motion, flickering, jittering, vibrating. The vacuum is not genuinely empty. At every single point in space, quantum fields are alive with zero-point energy, constantly shifting between potential and concrete presence. Even nothing is busy, and it is from this deep restlessness that all order elegantly arises. On the cosmic scale, that same quantum hum may be precisely what rapidly inflated the universe at its birth, stretching space and time themselves. Tiny fluctuations, when magnificently magnified by cosmic expansion, became the galaxies, the stars, and the very atoms that comprise your body. The infinite quiet of the early vacuum became the chorus of existence. From nothing, everything emerged, not through a miracle, but through balance, perfect symmetry between the positive and the negative, the visible and the unseen. The cosmos does not require an external spark to begin. It structurally carries its own ignition within. And yet, for all its constant motion, there is a profound, strange serenity to the universe. The fields hum, but they hum in harmony. Forces meticulously balance, probabilities gracefully smooth into patterns, and from the apparent chaos of quantum noise, order perpetually emerges. Galaxies majestically spiral in quiet perfection. Stars burn for billions of years with steady light. Life arises from the intricate interplay of randomness and unbreakable rule. And eventually, that life looks back up at the night sky and quietly wonders how it all began. You are an intrinsic part of that reflection. You are the universe actively observing its own energy through the unique lens of consciousness. Every single thought, every heartbeat, every complex dream is an expression of quantum energy, organized, momentary, and infinitely precious. You are not external to the physics that governs the cosmos. You are that physics, slowed and softened into life. It is deeply comforting to realize that in a universe fundamentally ruled by uncertainty, conservation offers a quiet, absolute promise. Nothing is ever truly lost. The energy that fuels your body was once the light of a star. The atoms that structurally build you were once scorching plasma drifting in the newborn cosmos. When your energy ultimately returns to the world, it will immediately adopt new forms, perhaps as heat, as light, as growth in something else. In the great exchange of existence, nothing is fundamentally wasted, and nothing truly ends. Perhaps that is what renders quantum energy so profoundly calming to contemplate. It does not suggest chaos or true randomness, but rather an endless continuity. Even when things physically dissolve, they persist in new, enduring patterns. Even when absolute silence appears to fall, motion continues underneath. The universe never genuinely stops moving. It only gently softens its voice. That pervasive quiet is everywhere, if you simply listen. In the gentle, persistent pull of gravity holding you to the earth. In the shimmer of sunlight reflecting on water. In the slow, majestic rotation of galaxies billions of light years away. Energy flows ceaselessly through all of it, connecting the past and the present, thought and matter, dust and brilliant flame. To truly understand quantum energy is to perceive that the universe is not structurally built from separate, isolated pieces, but from a single, unbroken whole. A symphony of quanta playing endlessly in variation. Sometimes the notes are bright and loud, the violent explosion of a supernova, the crackle of lightning. Sometimes they are soft, the quiet drift of a cloud, the steady rhythm of a heartbeat. But the music never stops. It simply changes tempo, changes key, changes form. And now, as our long journey gently draws to its quiet close, there is no need for a grand finale. Just the same calm, continuous hum that began it all. The background tone of existence, still perfectly vibrating, still intensely alive. From Dr. Reed's first crucial spark to the cosmic whisper of empty space, everything strictly follows the same single law. Energy flows, transforms, and endures. You do not need to retain every minute detail of the science in your mind to intuitively feel its truth. You can simply allow the powerful idea to settle, like light peacefully filtering through water. You can rest in the profound knowledge that beneath the stillness of your room, beneath the stillness of your own thoughts, the entire universe is gently moving, tirelessly maintaining balance. The same invisible energy that lights the stars hums softly within you. The same quantum fields that shaped distant galaxies ripple through your being. You are a vital part of the pattern, a fleeting yet eternal arrangement of the universe's own energy, experiencing itself for a little while as a human. And, as you peacefully drift towards sleep, you might take comfort in this singular truth, that the cosmos, vast and unending, is utterly at peace with its own motion. Its energy hums quietly, perpetually changing shape but never, ever ceasing. The night surrounding you is not empty. It is profoundly alive, filled with gentle vibrations, too small to see, too quiet to hear. The universe never truly stops moving. It only softens its voice. And now, in that profound softening, you can allow the silence to complete the thought. If you feel your eyelids growing heavy, allow the grand story of life on earth to wrap around you gently and guide you into calm. Close your eyes, take a deep breath, and slowly drift into sleep, into silence, into the boundless, timeless current where all life intertwines. Wishing you a quiet, comforting night.